Two-dimensional information creates three-dimensional reality through holographic encoding principles that compress complete spatial descriptions onto boundary surfaces, mathematical frameworks revealing how complex volumetric data structures can be perfectly represented through surface-based information storage systems. This dimensional compression demonstrates that apparent three-dimensional spatial experience may emerge from underlying two-dimensional information processing. Holographic principles suggesting that cosmic three-dimensional structure represents projection from boundary-encoded data rather than fundamental spatial dimensionality. Surface area entropy bounds establish maximum information storage capacity for spatial regions based on boundary area rather than interior volume. Bekenstein entropy limits revealing that information density scales with surface measurements in Planck units rather than volumetric capacity. These entropy relationships suggest that spatial volumes cannot contain more information than can be encoded on their boundary surfaces. Holographic constraints indicating that three-dimensional information storage represents redundant encoding of boundary-accessible information rather than fundamental volumetric information processing. Holographic reconstruction techniques demonstrate how complete three-dimensional images emerge from two-dimensional holographic plates through interference pattern encoding, optical holography providing physical demonstrations of dimensional information compression, where surface-recorded interference patterns contain sufficient information to reconstruct three-dimensional visual experiences. These reconstruction mechanisms establish experimental precedents for holographic information encoding, while revealing how two-dimensional data structures can generate convincing three-dimensional experiential content through appropriate information processing techniques. Mathematical holographic correspondence principles connect gravitational physics in spatial volumes to quantum field theory operating on boundary surfaces. Holographic duality relationships demonstrating exact mathematical equivalence between bulk gravitational dynamics and boundary field theory calculations. These correspondence relationships provide theoretical frameworks for understanding cosmic three-dimensional physics as emergent phenomena arising from boundary quantum field theory rather than fundamental three-dimensional physical processes operating within spatial volumes. Information theoretical foundations for holographic principles reveal connections between quantum information science and geometric physics. Quantum information entropy bounds naturally generating holographic entropy relationships through fundamental quantum mechanical information processing limitations. These information theoretical connections suggest that holographic principles reflect fundamental quantum information constraints rather than specific gravitational phenomena. Holographic effects emerging from universal quantum information processing limitations that apply across all physical systems regardless of specific gravitational or electromagnetic field configurations. Cosmic holographic applications investigate whether observable universe structure exhibits holographic characteristics consistent with boundary information encoding. Cosmic structure formation potentially operating through boundary information processing rather than bulk three-dimensional gravitational dynamics. These cosmic holographic scenarios provide alternative frameworks for understanding cosmic evolution, while demonstrating how cosmic structure could emerge from boundary quantum field theory through holographic projection mechanisms that transcend conventional three-dimensional cosmic physics. Quantum field theory modifications near boundaries create enhanced particle production and vacuum fluctuation effects that could generate apparent bulk physics phenomena through boundary quantum field dynamics. Boundary quantum effects potentially explaining cosmic structure formation through boundary-based particle creation and field evolution. These boundary quantum modifications suggest that cosmic physics reflects boundary quantum field theory, rather than bulk space-time quantum field dynamics. Boundary effects generating apparent three-dimensional physics through holographic projection mechanisms. Emergent gravity theories propose that gravitational phenomena emerge from more fundamental quantum information processing operating on boundary surfaces. Gravitational attraction and space-time curvature resulting from boundary quantum entanglement patterns, rather than fundamental geometric properties of three-dimensional space-time. These emergent gravity frameworks provide theoretical foundations for holographic cosmic models, while demonstrating how gravitational physics could represent emergent phenomena arising from boundary quantum information dynamics. Black hole physics applications of holographic principles demonstrate how gravitational systems naturally exhibit holographic information encoding. Black hole entropy, scaling with horizon surface area providing empirical evidence for holographic information storage in gravitational systems. These black hole holographic properties establish observational precedents for holographic physics, while revealing how gravitational systems naturally operate according to holographic information processing principles that transcend classical volumetric information storage mechanisms. String theoretical foundations for holographic principles provide microscopic physics frameworks for understanding holographic correspondence through fundamental string dynamics. String theory calculations demonstrating how higher dimensional gravitational physics projects onto lower dimensional boundary field theories through string theoretical mechanisms. These string theoretical foundations establish microscopic physical foundations for holographic principles, while creating connections between holographic physics and fundamental string theoretical descriptions of matter and energy. Laboratory holographic demonstrations create controlled holographic systems that exhibit information compression and three-dimensional reconstruction capabilities. Experimental holography providing empirical validation of holographic information processing principles while establishing technological applications for holographic information storage and retrieval. These laboratory demonstrations provide observational confirmation of holographic principles while revealing practical applications of holographic information processing techniques. Some believe holographic principles provide compelling explanations for cosmic fine-tuning and information paradox problems, based on boundary information encoding and dimensional reduction mechanisms, while others suggest that cosmic physics operates through fundamental three-dimensional processes that differ qualitatively from holographic boundary encoding scenarios. The applicability of holographic principles to cosmic physics continues to be investigated as holographic theory develops and cosmological observations achieve greater precision. Computational holographic models utilize computer simulations to investigate holographic information processing and boundary bulk correspondence relationships. Numerical holographic studies revealing computational requirements for holographic cosmic modeling while establishing theoretical limits on boundary computation capacity for cosmic evolution simulation. These computational approaches provide practical tools for holographic cosmic modeling while revealing computational constraints on holographic information processing mechanisms. Holographic entanglement entropy calculations connect quantum entanglement to geometric properties through holographic correspondence relationships. Entanglement entropy scaling with boundary area according to holographic principles that link quantum information to spatial geometry. These entanglement geometry connections provide mathematical tools for understanding holographic correspondence, while creating theoretical frameworks for quantum information applications to holographic cosmic modeling. The irony of holographic dimensional reduction lies in its creation of convincing three-dimensional reality from two-dimensional information processing. Conscious observers experiencing apparent three-dimensional cosmic structure that may represent sophisticated information processing occurring on cosmic boundary surfaces. Holographic cosmic reality concealing its own two-dimensional information processing origins through projection mechanisms that create three-dimensional spatial illusion, while cosmic evolution and cosmic structure formation operate through boundary quantum computation rather than bulk three-dimensional physics. Holographic projection creating cosmic dimensional illusion that appears fundamentally three-dimensional despite underlying two-dimensional information architecture. Black hole entropy revelations emerge from Bekenstein-Hawking calculations that demonstrate information content scaling with event horizon surface area rather than interior volume. Entropy relationships revealing S equals A over 4G, where horizon area determines maximum information storage capacity according to fundamental thermodynamic principles. These surface area scaling laws establish holographic entropy bounds for gravitational systems while challenging conventional volume-based intuitions about information storage. black hole thermodynamics, revealing that gravitational information processing operates through boundary encoding rather than volumetric information distribution throughout black hole interior regions. Hawking radiation temperature calculations reveal inverse relationships between black hole mass and thermal emission temperature. Massive black holes exhibiting lower temperatures, while smaller black holes radiate at higher temperatures according to thermodynamic relationships that connect black hole size to thermal emission characteristics. These temperature-mass relationships establish thermodynamic properties for black hole systems, while demonstrating how gravitational systems exhibit thermal behavior that reflects boundary physics rather than bulk interior thermal dynamics. Black hole thermodynamics operating through horizon boundary conditions. Information storage paradoxes arise when quantum mechanical unitarity requirements conflict with black hole information destruction. Quantum mechanics demanding information preservation, while black hole formation and evaporation suggest information loss through gravitational collapse and thermal radiation emission. These information paradox challenges reveal fundamental tensions between quantum mechanics and general relativity, while motivating holographic solutions that preserve quantum information through boundary encoding mechanisms that transcend apparent bulk information destruction during gravitational collapse processes. Entropy area. Relationships extend beyond black hole physics to cosmic horizons and general gravitational systems. Holographic entropy bounds applying universally to spatial regions with gravitational fields that create horizon boundaries and information isolation. These universal entropy bounds suggest that holographic principles represent fundamental aspects of gravitational physics, rather than phenomena specific to black hole systems. Holographic entropy scaling reflecting universal information processing limitations in curved space-time geometries. Black hole complementarity proposals attempt to resolve information paradox through observer-dependent descriptions, where different reference frames experience different physical phenomena near event horizons. Complementarity suggesting that information preservation and information destruction represent different perspective-dependent descriptions of identical physical processes. These complementarity scenarios provide theoretical frameworks for information preservation while maintaining consistency with both quantum mechanics and general relativity through observer-dependent physical law interpretation. Holographic correspondence applications to black hole physics demonstrate how black hole interior gravitational dynamics correspond exactly to quantum field theory operating on event horizon boundaries. ADS CFT correspondence providing mathematical tools for translating black hole physics problems into boundary field theory calculations. These correspondence relationships establish practical applications of holographic principles while revealing how black hole physics naturally exhibits holographic information processing characteristics through boundary bulk correspondence mechanisms. Black hole formation simulations reveal entropy production processes during gravitational collapse that create event horizons and establish horizon area relationships. Numerical relativity calculations demonstrating how matter collapse generates entropy, scaling according to horizon surface area rather than collapsing matter volume. These formation simulations provide computational evidence for holographic entropy bounds while revealing gravitational dynamics that naturally create boundary-based information processing during black hole formation processes. Quantum field theory near black hole horizons creates particle production and vacuum fluctuation effects that influence black hole thermodynamics and information processing. Quantum field modifications near horizon boundaries potentially affecting entropy calculations and information preservation mechanisms. These quantum field effects demonstrate how quantum mechanics modifies classical black hole thermodynamics while creating quantum mechanical foundations for holographic information processing near gravitational boundaries. Black hole evaporation through Hawking radiation creates information processing challenges where thermal radiation characteristics must preserve quantum information despite thermal emission properties that suggest information scrambling and information loss. These evaporation information challenges motivate holographic solutions where boundary encoding preserves quantum information, while maintaining consistency with thermal radiation observations and quantum mechanical unitarity requirements. Rotating black hole thermodynamics exhibits additional complexity through angular momentum contributions to entropy and temperature relationships. Kerr black hole physics, demonstrating how rotation affects holographic entropy bounds, while creating additional thermodynamic variables that influence information storage capacity. These rotating black hole systems provide extensions of holographic principles, while revealing how angular momentum affects boundary information processing and gravitational systems. Charged black hole solutions create electromagnetic contributions to thermodynamic relationships and entropy calculations. Reissner-Nordström black hole physics, demonstrating how electric charge affects holographic entropy bounds while creating additional complexity in boundary information processing. These charged black hole systems establish electromagnetic extensions of holographic principles, while revealing how multiple physical fields influence boundary information storage mechanisms. Some believe black hole entropy area relationships provide compelling evidence for holographic principles based on thermodynamic calculations and quantum field theory predictions. While others suggest that black hole thermodynamics represents unique gravitational phenomena that differ from general holographic information processing principles, the universality of holographic entropy bounds continues to be investigated as black hole physics understanding advances and quantum gravity theories develop. Primordial black hole scenarios investigate whether early universe black hole formation exhibits holographic entropy characteristics. Primordial black holes potentially demonstrating holographic principles during cosmic evolution, while contributing to cosmic structure formation through holographic information processing. These primordial scenarios provide cosmic applications of black hole holographic physics, while connecting black hole thermodynamics to cosmic evolution through early universe black hole formation. Black hole interior physics investigations explore whether holographic principles apply to space-time regions behind event horizons. Black hole interior geometry potentially exhibiting holographic characteristics despite causal disconnection from external boundary regions. These interior holographic studies provide theoretical extensions of boundary holographic principles, while investigating information processing mechanisms within gravitationally isolated space-time regions. The irony of black hole surface thermodynamics lies in its revelation that gravitational systems naturally operate according to holographic information processing principles. Black hole entropy, scaling demonstrating information storage through boundary encoding, while black hole interior regions remain causally isolated from boundary information processing. Gravitational collapse creating information processing systems that operate through surface area encoding despite volumetric gravitational dynamics. Black hole thermodynamics revealing holographic information architecture through gravitational systems that appear to operate through three-dimensional gravitational field dynamics, while actually processing information through two-dimensional boundary encoding mechanisms that determine thermodynamic properties and information storage capacity. ADS as CFT correspondence emerges as mathematical proof of holographic duality through exact equivalence between anti-de Sitter space-time gravitational physics and conformal field theory operating on ADS boundary surfaces. Maldaceno's discovery revealing precise mathematical relationships that translate gravitational calculations into boundary quantum field theory computations. This correspondence demonstrates that gravitational phenomena in curved spacetime can be completely described through quantum field theory on lower dimensional boundaries. Holographic duality providing computational tools for solving gravitational physics problems through boundary field theory, techniques that transcend dimensional limitations. Anti-de Sitter spacetime geometry exhibits negative cosmological constant that creates hyperbolic spatial curvature with well-defined boundary structure. ADS geometry providing mathematical frameworks for holographic correspondence where bulk gravitational dynamics correspond systematically to boundary conformal field theory evolution. These geometric properties establish spatial frameworks for holographic duality while creating mathematical structures that support precise correspondence relationships between gravitational physics and quantum field theory through dimensional reduction mechanisms. Conformal field theory characteristics include scale invariance and conformal symmetry that generate gravitational phenomena through boundary quantum field dynamics. CFT calculations producing bulk gravitational effects including black hole formation, gravitational wave propagation, and space-time curvature evolution through boundary field theory computations. These conformal field properties demonstrate how quantum field theory naturally generates gravitational phenomena while establishing theoretical foundations for gravitational emergence from boundary quantum dynamics. Mathematical dictionary translations between ADS gravity and CFT provide systematic correspondences that connect gravitational concepts to field theory concepts. Holographic dictionary entries establishing relationships between bulk gravitational fields and boundary operators, between gravitational dynamics and field theory correlation functions, between space-time geometry and quantum field theory states. These translation relationships create practical tools for holographic calculations while demonstrating systematic connections between gravitational and quantum field theoretical descriptions of physical phenomena. String theory foundations for ADS-CFT correspondence provide microscopic physical mechanisms for holographic duality through string theoretical dynamics that naturally generate both gravitational physics and boundary field theory. String theory calculations demonstrating how fundamental string interactions create holographic correspondence relationships. These string theoretical foundations establish microscopic physics for holographic duality while connecting ADS-CFT correspondence to fundamental string theoretical descriptions of matter, energy, and gravitational interactions. Large N-limit applications to ADS-CFT correspondence investigate holographic duality and strongly coupled quantum field theories. Large N expansion techniques revealing holographic relationships that become exact in specific parameter limits while providing systematic approximation methods for holographic calculations. These large N techniques create practical computational approaches for holographic correspondence while establishing parameter regimes where holographic duality achieves mathematical exactness. Gauge theory applications of ADS-CFT correspondence utilize holographic duality to investigate strongly coupled gauge field theories through gravitational calculations. Gauge theory problems that remain intractable through conventional field theory techniques becoming solvable through holographic gravitational methods. These gauge theory applications demonstrate practical utility of holographic correspondence, while revealing how boundary quantum field theories can exhibit strongly coupled dynamics that correspond to classical gravitational physics. Black hole correspondence in ADS-CFT duality connects gravitational black hole formation and evaporation to boundary field theory, thermal transitions, and quantum information processing. Black hole physics becoming accessible through boundary field theory, calculations that preserve quantum information while reproducing gravitational thermodynamic behavior. These black hole applications provide holographic solutions to information paradox problems while demonstrating how gravitational collapse phenomena correspond to boundary quantum field theory dynamics. Entanglement entropy calculations in ADS or CFT correspondence reveal geometric interpretations for quantum entanglement through holographic geometric constructions. Boundary quantum entanglement corresponding to bulk geometric surfaces that minimize area according to holographic entanglement entropy formulas. These entanglement geometry relationships provide geometric interpretations for quantum information, while creating mathematical tools for understanding quantum entanglement through holographic geometric analysis. Holographic renormalization techniques address mathematical divergences in ADS-CFT calculations through systematic regularization procedures that extract finite physical predictions from holographic correspondence relationships. Renormalization methods providing mathematical tools for practical holographic calculations while maintaining consistency between boundary field theory and bulk gravitational physics. These renormalization approaches establish computational frameworks for holographic duality, while addressing mathematical challenges in holographic correspondence calculations. Wilson loop calculations in ADS-CFT correspondence connect boundary gauge theory observables to bulk gravitational geometric constructions. Wilson loops corresponding to minimal surfaces in ADS spacetime according to holographic prescription relationships that translate gauge theory calculations into geometric area computations. These Wilson loop correspondences provide specific examples of holographic dictionary entries while demonstrating how gauge theory observables correspond to gravitational geometric quantities. Some believe ADS/CFT correspondence provides definitive mathematical proof of holographic principles based on exact correspondence relationships and string theoretical foundations, while others suggest that ADS/CFT duality represents specific mathematical relationships that may not generalize to realistic cosmological spacetimes with different geometric and field theory characteristics. The applicability of ADS/CFT correspondence to realistic physics continues to be investigated as holographic theory develops. Finite temperature applications of ADS/CFT correspondence investigate thermal field theory through holographic black hole physics. Finite temperature boundary field theory corresponding to bulk space-time containing black holes whose thermodynamic properties reproduce boundary thermal behavior. These thermal applications provide holographic descriptions of finite temperature field theory while connecting thermal physics to gravitational black hole thermodynamics through holographic correspondence mechanisms. Cosmological applications of ADS/CFT correspondence explore whether holographic duality principles apply to realistic cosmological spacetimes. Cosmological holography investigating extensions of ADS/CFT correspondence to universe models with positive cosmological constant and expanding spacetime geometry. These cosmological applications provide theoretical frameworks for holographic cosmology while extending holographic duality beyond ADS spacetime to realistic universe models. The irony of ADS/CFT mathematical proof lies in its demonstration of exact holographic duality through anti-de Sitter spacetime that differs significantly from realistic universe geometry. Mathematical proof of holographic principles operating within theoretical spacetime models that may not directly apply to observable cosmic spacetime, while providing compelling evidence for holographic information processing in gravitational systems. ADS/CFT correspondence establishing holographic duality as mathematical reality, while remaining uncertain about holographic applicability to realistic cosmological physics. Exact mathematical holographic proof existing within theoretical frameworks that transcend direct observational verification in realistic universe geometry. Quantum information storage approaches fundamental limits when cosmic boundary surfaces achieve maximum information density, according to holographic entropy bounds. Bekenstein limits revealing that cosmic horizon areas determine information storage capacity through Planck unit measurements rather than volumetric information processing mechanisms. These information density bounds suggest that cosmic regions cannot store more quantum information than can be encoded on their boundary surfaces. Cosmic information processing operating at theoretical limits imposed by quantum mechanical information theory and gravitational physics through boundary encoding constraints. Planck scale discretization creates fundamental information units where each Planck area element on cosmic boundary surfaces encodes specific quantum information content. Quantum information density achieving maximum possible values when boundary encoding utilizes complete Planck area coverage for information storage. These Planck unit relationships establish quantum mechanical foundations for cosmic information processing, while revealing discrete information architecture underlying continuous cosmic boundary surfaces through quantum geometric information encoding mechanisms. Cosmic horizon information calculations estimate total information storage capacity within observable universe regions. Cosmic boundary area measurements in Planck units determining maximum cosmic information content according to holographic entropy, bounds that apply universally to cosmic regions with gravitational fields. These cosmic information estimates reveal enormous information processing capacity within cosmic boundary systems, while establishing quantitative frameworks for understanding cosmic information architecture through boundary surface area calculations. Quantum error correction mechanisms operating on cosmic boundaries provide theoretical frameworks for information preservation against cosmic evolution, perturbations, and environmental decoherence. Cosmic quantum information requiring protection mechanisms that maintain information coherence despite cosmic expansion and cosmic structure formation processes. These error correction frameworks suggest that cosmic information processing operates through quantum mechanical protection systems while maintaining information integrity across cosmic evolution timescales through boundary, quantum error correction mechanisms. Information theoretical entropy bounds establish maximum information content for cosmic regions through statistical mechanical relationships between information theory and thermodynamics. Quantum information entropy approaching thermodynamic entropy limits when cosmic systems achieve maximum information density. These entropy relationships connect quantum information theory to cosmic thermodynamics, while providing theoretical foundations for understanding cosmic information processing through statistical mechanical frameworks that govern both quantum information and cosmic thermal evolution. Cosmic microwave background information content approaches holographic bounds, when cosmic background radiation information density achieves maximum values permitted by cosmic horizon area constraints. Cosmic thermal radiation carrying information content that saturates theoretical limits for boundary information storage. These cosmic background information measurements provide observational constraints on cosmic information processing while revealing cosmic information density characteristics that approach theoretical maximum values permitted by holographic entropy bounds. Quantum entanglement networks across cosmic boundaries create information correlation patterns that transcend local information processing limitations. Cosmic quantum entanglement potentially maintaining information coherence across cosmic distances through quantum correlation mechanisms that operate independently of classical information transmission. These cosmic entanglement networks suggest that cosmic information processing transcends local boundary limitations while creating cosmic-scale quantum information correlation systems through boundary quantum entanglement mechanisms. Black hole information storage provides cosmic examples of boundary information encoding where gravitational systems achieve maximum information density through horizon surface area encoding. Black hole systems demonstrating practical applications of holographic information storage in cosmic gravitational environments. These black hole information examples establish observational precedents for cosmic boundary information processing while revealing how gravitational systems naturally achieve maximum information density through boundary encoding mechanisms. Cosmic information flow investigations explore information transmission and information processing rates across cosmic boundary systems. Cosmic information dynamics potentially operating through boundary information processing that transcends bulk information transmission limitations through quantum mechanical information processing mechanisms. These information flow studies provide theoretical frameworks for understanding cosmic information dynamics while revealing information processing capabilities of cosmic boundary systems through quantum information theoretical analysis. Computational complexity measures for cosmic information processing investigate computational resource requirements for cosmic boundary information processing. Cosmic computation potentially operating at theoretical limits imposed by boundary information storage capacity and quantum information processing constraints. These complexity studies establish theoretical limits on cosmic computation while revealing computational capabilities and computational limitations of cosmic boundary information processing systems through information theoretical complexity analysis. Cosmic information preservation mechanisms address information conservation requirements during cosmic evolution and cosmic structure formation. Cosmic information content requiring preservation mechanisms that maintain quantum information despite cosmic expansion and cosmic gravitational evolution. These preservation studies provide theoretical frameworks for cosmic information conservation while investigating quantum mechanical mechanisms that protect cosmic information against cosmic evolution perturbations and environmental decoherence effects. Some believe cosmic information processing operates at holographic entropy bounds based on quantum information theoretical calculations and cosmic boundary area measurements, while others suggest that cosmic information processing utilizes only small fractions of theoretical maximum information capacity despite holographic bound calculations. The efficiency of cosmic information utilization continues to be investigated as quantum information theory develops and cosmic observation techniques advance. Quantum computation applications to cosmic information processing explore whether cosmic evolution represents quantum computational processes operating on cosmic boundary systems. Cosmic computation potentially achieving quantum computational capabilities that transcend classical computational limitations through quantum mechanical information processing mechanisms. These quantum computational approaches provide theoretical frameworks for understanding cosmic evolution as quantum computation, while revealing quantum computational capabilities of cosmic boundary information processing systems. Information geometry applications to cosmic boundary systems investigate mathematical relationships between information theoretical measures and geometric properties of cosmic boundaries. Information geometry providing mathematical tools for understanding cosmic boundary information processing through differential geometric analysis of information theoretical structures. These geometric approaches create mathematical frameworks for cosmic information analysis, while connecting information theory to cosmic geometric properties through information geometric mathematical techniques. The irony of cosmic information limits lies in their revelation of cosmic information processing capabilities that approach theoretical maximum values while remaining largely unutilized for conscious information processing. Cosmic boundary systems achieving maximum information density through quantum mechanical information encoding, while conscious observers access only infinitesimal fractions of cosmic information capacity. Cosmic information architecture operating at fundamental quantum mechanical limits, while conscious information processing operates far below cosmic information processing capabilities. Cosmic information storage achieving theoretical maximum capacity through boundary encoding, while conscious information access remains limited to local information processing that transcends cosmic information architecture limitations. String theory holographic emergence demonstrates how higher dimensional gravitational dynamics naturally project onto lower dimensional boundary quantum field theories through fundamental string theoretical mechanisms. String calculations revealing mathematical pathways from higher dimensional string dynamics to lower dimensional effective field theories. These string theoretical foundations provide microscopic physics explanations for holographic correspondence, while establishing connections between fundamental string dynamics and emergent holographic phenomena through dimensional reduction mechanisms that operate according to string theoretical principles rather than purely geometric projection effects. Higher dimensional string compactification creates lower dimensional effective theories through geometric compactification mechanisms that reduce string theoretical dynamics from 10-dimensional string space-time to 4-dimensional effective physics. Compactification generating holographic relationships between higher dimensional string physics and lower dimensional field theory through dimensional reduction. These compactification processes demonstrate how string theory naturally generates holographic correspondence through dimensional reduction mechanisms while creating theoretical frameworks for understanding cosmic dimensionality as emergent from higher dimensional string theoretical physics. D-brane physics in string theory exhibits holographic characteristics where brane dynamics correspond to gauge theory on brane surfaces. D-brane systems demonstrating how string theoretical objects naturally exhibit boundary bulk correspondence through brane gauge theory correspondence. These D-brane holographic relationships provide string theoretical examples of holographic duality, while establishing microscopic string theoretical mechanisms for boundary bulk correspondence through fundamental string theoretical objects, rather than purely geometric holographic projections. String theoretical calculations demonstrate exact correspondence between higher dimensional gravitational string dynamics and lower dimensional gauge field theories, string perturbation theory generating both gravitational effects and gauge theory phenomena through unified string theoretical frameworks. These unified string calculations provide theoretical foundations for holographic correspondence, while revealing how string theory naturally generates both gravitational physics and boundary field theory through fundamental string dynamics that transcend classical gravitational and field theoretical descriptions. Extra-dimensional string physics creates holographic relationships through dimensional hierarchy mechanisms that generate lower dimensional physics from higher dimensional string dynamics. Extra dimensions providing geometric frameworks for holographic projection, while string dynamics provide physical mechanisms for dimensional correspondence. These extra-dimensional frameworks establish theoretical foundations for cosmic holographic scenarios, while demonstrating how string theory naturally incorporates dimensional reduction and holographic correspondence through fundamental string theoretical principles. M-theory applications to holographic physics investigate 11-dimensional supergravity correspondence to lower-dimensional field theories. M-theory providing extended frameworks for holographic duality that transcend string theoretical limitations while incorporating membrane dynamics and higher-dimensional gravitational physics. These M-theory extensions demonstrate theoretical developments in holographic correspondence, while revealing connections between membrane physics and holographic boundary bulk correspondence through higher-dimensional gravitational dynamics. String theoretical black hole physics exhibits holographic information processing where black hole formation and evaporation correspond to boundary gauge theory thermal transitions, string black holes demonstrating microscopic string theoretical mechanisms for black hole thermodynamics and information processing. These string black hole applications provide microscopic foundations for black hole holographic physics, while revealing how string theory resolves black hole information paradox problems through holographic information preservation mechanisms. Gravitational wave correspondence in string theory connects bulk gravitational wave propagation to boundary field theory, correlation functions, string theoretical gravitational waves corresponding to specific boundary gauge theory, observables through holographic dictionary relationships. These gravitational wave correspondences provide specific examples of holographic duality applications, while demonstrating how gravitational phenomena correspond to boundary field theory dynamics through string theoretical holographic mechanisms. String cosmology applications investigate whether cosmic evolution exhibits string theoretical holographic characteristics. Cosmic inflation and cosmic structure formation potentially operating through string theoretical holographic mechanisms that connect cosmic bulk dynamics to boundary string field theory. These cosmological applications provide theoretical frameworks for string theoretical cosmology, while extending holographic correspondence to realistic cosmic evolution scenarios through string theoretical mechanisms. Supersymmetric string models create enhanced holographic correspondence through supersymmetry relationships that connect gravitational supersymmetry to boundary field theory, supersymmetry, supersymmetric holographic duality exhibiting enhanced mathematical control and theoretical consistency compared to non-supersymmetric holographic scenarios. These supersymmetric models provide theoretical advantages for holographic calculations while demonstrating how supersymmetry enhances holographic correspondence through mathematical relationships that transcend non-supersymmetric holographic limitations. String field theory applications to holographic physics investigate whether fundamental string field dynamics exhibit holographic characteristics. String field theory potentially providing field theoretical descriptions of holographic correspondence through string field rather than string perturbation theoretical approaches. These string field applications provide alternative theoretical frameworks for holographic physics, while extending holographic correspondence to non-perturbative string theoretical regimes through string field theoretical methods. Some believe string theory provides definitive theoretical foundations for holographic physics based on mathematical consistency and unified theoretical frameworks, while others suggest that string theoretical holographic correspondence remains limited to specific theoretical scenarios that may not apply to realistic physics despite mathematical elegance. The universality of string theoretical holographic mechanisms continues to be investigated as string theory develops and observational constraints on string theoretical predictions improve. Topological string theory applications to holographic physics investigate whether topological string dynamics exhibit holographic characteristics. Topological strings potentially providing simplified frameworks for understanding holographic correspondence through topological rather than dynamical string theoretical mechanisms. These topological applications demonstrate mathematical approaches to holographic physics, while revealing connections between topological string theory and holographic correspondence through mathematical rather than physical correspondence mechanisms. Non-critical string theory extensions explore holographic correspondence in string theoretical models that operate in non-critical dimensions. Non-critical strings potentially providing theoretical frameworks for realistic holographic correspondence that transcends critical string theoretical limitations. These non-critical extensions demonstrate theoretical flexibility in string theoretical holographic physics while investigating holographic correspondence mechanisms that operate beyond standard critical string theoretical frameworks. The irony of string theoretical holographic emergence lies in its requirement for higher dimensional string physics to generate lower dimensional holographic reality. String theory creating holographic correspondence through fundamental physics that operates in dimensions beyond direct observational access, while generating observable physics through dimensional reduction. String theoretical holographic mechanisms operating through theoretical frameworks that transcend empirical verification while providing mathematical foundations for holographic physics that could determine observable reality. Higher dimensional string physics creating lower dimensional holographic illusion through theoretical mechanisms that remain beyond direct experimental investigation despite potentially determining fundamental nature of observable physical reality through holographic projection from higher dimensional string theoretical dynamics. Cosmic horizon holographic encoding suggests that observable universe boundaries contain complete cosmic information encoded on cosmic horizon surfaces. Three-dimensional cosmic structure potentially emerging from two-dimensional boundary information processing, rather than fundamental three-dimensional cosmic physics operating within cosmic volumes. This cosmic holographic scenario proposes that cosmic evolution, cosmic structure formation, and cosmic physical phenomena represent projections from cosmic boundary information processing. Observable cosmic reality emerging from cosmic horizon quantum field theory through holographic projection mechanisms that transcend three-dimensional cosmic physics limitations. Observable universe boundaries create natural cosmic horizon surfaces where cosmic information encoding could operate according to holographic principles. Cosmic horizon area measurements providing cosmic information storage capacity, estimates that approach holographic entropy bounds for cosmic regions. These cosmic boundary measurements suggest that cosmic information processing operates through cosmic horizon encoding, while cosmic interior three-dimensional physics represents emergent phenomena arising from cosmic boundary quantum information dynamics rather than fundamental cosmic volumetric physics. Cosmic microwave background analysis reveals uniform thermal radiation characteristics that could result from cosmic boundary information processing rather than three-dimensional cosmic thermal evolution. Cosmic background radiation potentially preserving signatures of cosmic boundary quantum field theory that generated cosmic thermal characteristics through holographic projection. These cosmic background signatures provide observational frameworks for testing cosmic holographic scenarios while revealing cosmic thermal properties that could reflect cosmic boundary information processing rather than bulk cosmic thermal dynamics. Cosmic structure formation through boundary information processing could generate galactic and cosmic large-scale structure through cosmic boundary quantum field theory dynamics. Cosmic structure development potentially operating through boundary information processing that creates apparent three-dimensional cosmic structure through holographic projection mechanisms. These boundary structure formation scenarios provide alternative frameworks for cosmic evolution while demonstrating how cosmic structure could emerge from cosmic boundary dynamics rather than three-dimensional cosmic gravitational physics. Cosmic expansion holographic interpretations investigate whether cosmic expansion represents coordinate effects within holographic cosmic models rather than fundamental cosmic spatial expansion. Cosmic expansion potentially reflecting boundary information processing dynamics rather than genuine cosmic spatial growth through three-dimensional cosmic expansion mechanisms. These holographic expansion interpretations provide alternative explanations for cosmic expansion observations, while suggesting that cosmic expansion represents holographic projection effects rather than fundamental cosmic spatial evolution. Dark matter holographic explanations propose that invisible matter effects result from cosmic boundary information processing artifacts rather than fundamental dark matter particle distributions within cosmic volumes. Dark matter gravitational effects potentially arising from cosmic boundary encoding rather than exotic matter particles distributed throughout cosmic three-dimensional space. These holographic dark matter scenarios provide alternative explanations for dark matter observations, while eliminating requirements for exotic matter particles through cosmic boundary information processing mechanisms. Dark energy holographic scenarios investigate whether cosmic acceleration results from cosmic boundary information processing rather than exotic dark energy components within cosmic volumes. Cosmic acceleration potentially reflecting cosmic boundary dynamics rather than fundamental dark energy field evolution throughout cosmic space-time. These holographic dark energy interpretations provide alternative explanations for cosmic acceleration while eliminating requirements for exotic energy components through cosmic boundary information processing effects. Cosmic fine-tuning holographic resolution suggests that cosmic parameter optimization occurs through cosmic boundary information processing that selects cosmic parameters for optimal cosmic structure formation and cosmic biological evolution. Cosmic fine-tuning potentially reflecting cosmic boundary optimization rather than anthropic selection or multiverse parameter variation. These holographic fine-tuning scenarios provide alternative explanations for cosmic parameter precision, while demonstrating how cosmic boundary information processing could optimize cosmic evolution for cosmic complexity development. Cosmic information paradox holographic resolution addresses cosmic information conservation requirements through cosmic boundary information preservation mechanisms. Cosmic information content potentially preserved through cosmic boundary encoding despite apparent cosmic information destruction during cosmic evolution and cosmic structure formation. These cosmic information preservation mechanisms provide holographic solutions to cosmic information conservation problems, while maintaining quantum mechanical information conservation through cosmic boundary information processing. Cosmic observer effects in holographic cosmology investigate whether conscious cosmic observation influences cosmic boundary information processing. Conscious observation potentially affecting cosmic evolution through cosmic boundary information processing that responds to conscious measurement and conscious observation. These cosmic observer scenarios provide frameworks for understanding conscious participation in cosmic evolution through cosmic boundary information processing that transcends purely objective cosmic evolution independent of conscious observation. Cosmic multiverse holographic connections propose that parallel cosmic evolution operates through shared cosmic boundary information processing networks. Multiverse interactions, potentially occurring through cosmic boundary information processing that connects different cosmic evolution scenarios through shared boundary information networks. These multiverse holographic scenarios provide frameworks for cosmic multiverse interactions, while demonstrating how cosmic boundary information processing could facilitate multiverse communication and multiverse evolution coordination. Some believe cosmic horizon holographic encoding provides compelling explanations for cosmic fine-tuning and cosmic evolution based on cosmic boundary information processing capabilities and holographic cosmic modeling, while others suggest that cosmic physics operates through fundamental three-dimensional mechanisms that differ qualitatively from cosmic boundary information processing scenarios. The viability of cosmic holographic models continues to be investigated as holographic theory develops and cosmological observations achieve greater precision. Cosmic evolution computational complexity investigates whether cosmic boundary information processing achieves computational capabilities sufficient for cosmic structure formation and cosmic biological evolution. Cosmic computation potentially operating through cosmic boundary information processing that transcends classical computational limitations through quantum computational mechanisms. These cosmic computational studies provide theoretical frameworks for understanding cosmic evolution as cosmic computation while revealing computational capabilities of cosmic boundary information processing systems. Cosmic consciousness holographic emergence investigates whether conscious experience emerges from cosmic boundary information processing rather than local biological neural computation. Consciousness potentially representing cosmic boundary information processing that creates conscious experience through holographic projection rather than fundamental biological neural information processing. These consciousness holographic scenarios provide alternative frameworks for understanding consciousness through cosmic boundary information processing, while connecting consciousness to cosmic holographic evolution. The irony of cosmic holographic encoding lies in its suggestion that cosmic three-dimensional experience represents illusion created by cosmic boundary information processing. Conscious observers experiencing apparent cosmic three-dimensional reality, while cosmic evolution operates through cosmic boundary computation that creates cosmic three-dimensional illusion through holographic projection. Cosmic reality emerging from cosmic boundary information processing, while appearing to operate through three-dimensional cosmic physics that conceals underlying cosmic boundary information architecture. Cosmic holographic encoding creating cosmic reality through boundary computation, while conscious cosmic observers remain unaware of cosmic boundary information processing that generates cosmic three-dimensional experience through holographic cosmic projection mechanisms. Emergent spacetime arises from quantum entanglement networks, where spatial distance relationships reflect quantum correlation patterns rather than fundamental geometric properties. Space-time geometry emerging from quantum information processing through entanglement, connectivity that creates effective geometric relationships between spatial regions. These quantum entanglement foundations suggest that cosmic spatial structure represents emergent phenomena arising from underlying quantum correlation networks rather than fundamental geometric space-time manifolds. Spatial distance and temporal relationships emerging from quantum entanglement patterns through information theoretical mechanisms that transcend classical geometric spacetime descriptions. Quantum entanglement entropy calculations reveal geometric interpretations where entanglement measures correspond to spatial area measurements according to holographic entanglement entropy formulas. Quantum entanglement between spatial regions scaling with boundary area rather than bulk volume measurements. These entanglement geometry relationships provide mathematical frameworks connecting quantum information to spatial geometry while demonstrating how geometric properties emerge from quantum entanglement rather than representing fundamental geometric characteristics of spacetime manifolds. Tensor network models demonstrate how quantum entanglement patterns generate effective spacetime geometry through network connectivity structures. Tensor networks creating geometric emergence through quantum entanglement connectivity that reproduces gravitational physics and space-time curvature effects. These network geometric models provide computational frameworks for understanding space-time emergence, while revealing how quantum entanglement naturally generates geometric relationships through information theoretical mechanisms rather than fundamental geometric space-time properties. EPR correspondence proposes that quantum entanglement corresponds to microscopic wormhole connections, Einstein-Rosen bridges providing geometric interpretations for quantum entanglement that transcends mysterious action at a distance through space-time connectivity. This entanglement wormhole correspondence suggests that quantum correlations operate through space-time geometric connections rather than non-local quantum mechanical effects. Quantum entanglement reflecting space-time topology rather than fundamental quantum mechanical non-locality that violates relativistic causality limitations. Emergent gravity theories propose that gravitational phenomena emerge from quantum entanglement networks rather than fundamental space-time curvature. Gravitational attraction resulting from quantum entanglement patterns that create effective gravitational forces through quantum information processing mechanisms. These emergent gravity frameworks provide alternative explanations for gravitational physics, while demonstrating how gravitational phenomena could represent emergent quantum information effects rather than fundamental geometric space-time curvature created by mass-energy distributions. Quantum error correction relationships to space-time geometry investigate whether geometric properties emerge from quantum error correction mechanisms operating within quantum entanglement networks. Space-time geometry potentially representing quantum error correction structures that maintain quantum information coherence through geometric relationships. These error correction frameworks suggest that space-time geometry serves quantum information processing functions while providing geometric stability for quantum entanglement networks through error correction mechanisms. CFT entanglement applications demonstrate how boundary quantum entanglement generates bulk space-time geometry through holographic correspondence. boundary entanglement patterns corresponding to bulk geometric structures according to holographic entanglement entropy calculations. These holographic entanglement relationships provide specific examples of quantum entanglement generating space-time geometry while establishing mathematical frameworks for understanding geometric emergence from quantum information processing through holographic correspondence mechanisms. Cosmic structure formation through entanglement networks could operate through quantum entanglement evolution that creates apparent cosmic structure formation through quantum correlation development. Cosmic structure potentially reflecting quantum entanglement network evolution, rather than classical gravitational structure formation through matter distribution and gravitational attraction. These entanglement structure formation scenarios provide alternative frameworks for cosmic evolution, while demonstrating how quantum entanglement could generate cosmic structure through quantum information dynamics. Quantum field theory, vacuum entanglement creates quantum correlation networks throughout spacetime that could provide foundations for spacetime geometry emergence. Vacuum entanglement establishing baseline quantum correlation structures that support geometric relationships between spacetime points. These vacuum entanglement foundations suggest that spacetime geometry emerges from quantum field theory, vacuum structure, rather than representing fundamental geometric properties independent of quantum field theoretical effects. Black hole entanglement applications investigate whether black hole spacetime geometry emerges from quantum entanglement networks. Black hole interior and exterior spacetime regions potentially connected through quantum entanglement rather than classical geometric spacetime relationships. These black hole entanglement scenarios provide frameworks for understanding black hole geometry through quantum entanglement while addressing black hole information paradox problems through entanglement-based information preservation mechanisms. Cosmological entanglement networks explore whether cosmic evolution operates through quantum entanglement development across cosmic distances. Cosmic entanglement potentially creating cosmic correlation networks that influence cosmic structure formation and cosmic evolution through quantum information processing mechanisms. These cosmic entanglement scenarios provide frameworks for understanding cosmic evolution through quantum entanglement, while creating connections between cosmic physics and quantum information science through cosmic scale quantum correlation networks. Some believe quantum entanglement provides fundamental explanations for space-time geometry emergence based on entanglement entropy calculations and tensor network models, while others suggest that space-time geometry represents fundamental physical properties that transcend quantum entanglement despite mathematical relationships between entanglement and geometry. The relationship between quantum entanglement and space-time geometry continues to be investigated as quantum information theory develops and quantum gravity understanding advances. Entanglement swapping applications to space-time geometry investigate whether geometric relationships can be modified through quantum entanglement manipulation. Entanglement swapping potentially affecting space-time geometry through quantum information processing that transcends classical geometric manipulation. These entanglement manipulation scenarios provide theoretical frameworks for understanding space-time geometry modification through quantum information processing while revealing connections between quantum information control and geometric space-time properties. Quantum teleportation relationships to space-time geometry explore whether quantum information transmission affects geometric relationships between spatial regions. Quantum teleportation potentially operating through space-time geometric modification rather than purely quantum information theoretical mechanisms. These teleportation scenarios provide alternative interpretations for quantum information transmission while connecting quantum information effects to space-time geometry modification through quantum entanglement mechanisms. The irony of entanglement geometric emergence lies in its creation of apparent geometric space-time reality from non-geometric quantum information processing. Quantum entanglement networks generating convincing geometric space-time experience while operating through quantum correlation patterns that transcend geometric description. Spatial distance relationships emerging from quantum entanglement connectivity while appearing to represent fundamental geometric space-time properties. Quantum entanglement creating geometric space-time illusion through information theoretical mechanisms that remain invisible to geometric spacetime observation, despite generating all observable geometric relationships through quantum information processing networks that transcend classical geometric spacetime architecture, while creating geometric spacetime experience through emergent quantum entanglement dynamics. Holographic quantum error correction emerges from theoretical frameworks that demonstrate how quantum information preservation operates through boundary encoding systems that maintain information coherence despite bulk space-time perturbations and environmental decoherence effects. Quantum error correction mechanisms protecting holographic information through redundant encoding across boundary degrees of freedom. These error correction systems suggest that holographic correspondence includes built-in protection mechanisms that preserve quantum information through distributed boundary encoding while maintaining consistency between boundary quantum field theory and bulk gravitational physics through quantum mechanical information protection. Quantum error correction codes applied to holographic systems utilize mathematical frameworks from quantum information science to understand how boundary quantum field theories preserve information despite bulk gravitational dynamics that could potentially destroy quantum information. Holographic error correction operating through quantum mechanical protection mechanisms that transcend classical information storage limitations. These quantum protection frameworks provide theoretical foundations for understanding holographic information preservation, while demonstrating how quantum mechanical error correction naturally emerges within holographic correspondence relationships. Boundary bulk information preservation requires quantum mechanical mechanisms that maintain information coherence across dimensional reduction. Holographic correspondence demanding information conservation despite apparent dimensional compression that could potentially eliminate information through projection effects. These information preservation requirements suggest that holographic correspondence operates through quantum error correction rather than simple geometric projection, quantum mechanical protection ensuring information conservation during holographic dimensional reduction processes. Entanglement-based error correction in holographic systems operates through quantum entanglement networks that provide redundant information encoding across boundary degrees of freedom. Quantum entanglement creating distributed information storage that protects against local boundary perturbations while maintaining global information coherence. These entanglement protection mechanisms demonstrate how quantum correlation networks naturally provide error correction capabilities while establishing theoretical foundations for robust holographic information processing through quantum entanglement-based protection systems. ADS-CFT error correction applications investigate specific quantum error correction mechanisms operating within anti-de Sitter spacetime holographic correspondence. ADS-CFT duality, exhibiting quantum error correction properties that preserve boundary field theory information despite bulk gravitational dynamics including black hole formation and gravitational perturbations. These specific error correction examples provide computational frameworks for understanding holographic quantum protection, while revealing how established holographic correspondence naturally incorporates quantum error correction mechanisms. Black hole information preservation through holographic error correction addresses quantum information paradox problems by demonstrating how boundary encoding preserves quantum information despite apparent bulk information destruction during black hole formation and evaporation. Holographic error correction maintaining quantum mechanical unitarity through boundary information protection. These black hole applications provide practical examples of holographic error correction, while resolving fundamental conflicts between quantum mechanics and gravitational physics through quantum mechanical information preservation mechanisms. Tensor network error correction models demonstrate how quantum error correction operates within mathematical frameworks that reproduce holographic correspondence. Tensor network quantum codes providing computational tools for understanding holographic error correction, while creating practical algorithms for holographic quantum information protection. These computational approaches establish mathematical foundations for holographic error correction, while providing numerical tools for investigating quantum protection mechanisms within holographic systems. Cosmic holographic error correction scenarios investigate whether cosmic boundary information processing includes quantum error correction mechanisms that protect cosmic information against cosmic evolution perturbations and environmental decoherence. cosmic quantum information requiring protection mechanisms that maintain information coherence across cosmic evolution timescales. These cosmic error correction frameworks provide theoretical approaches for understanding cosmic information preservation, while extending holographic error correction principles to cosmic scale information processing systems. Quantum redundancy mechanisms in holographic systems create multiple information copies distributed across boundary degrees of freedom. Quantum redundancy providing protection against information loss through distributed encoding that transcends local information destruction while maintaining global information accessibility. These redundancy mechanisms demonstrate how holographic systems naturally incorporate quantum information protection while providing theoretical frameworks for understanding distributed quantum information storage and protection. Error correction threshold calculations for holographic systems investigate quantum error correction performance limits and optimal protection strategies. Holographic error correction achieving specific performance thresholds that determine information preservation capabilities under various perturbation and decoherence scenarios. These threshold calculations provide quantitative frameworks for holographic error correction, while establishing performance limits and optimization strategies for holographic quantum information protection systems. Decoherence resistance in holographic quantum codes addresses environmental perturbation effects on holographic information processing. Holographic error correction systems exhibiting enhanced decoherence resistance compared to conventional quantum error correction through distributed boundary encoding and quantum entanglement protection mechanisms. These decoherence studies provide theoretical frameworks for understanding holographic information stability, while revealing environmental protection capabilities of holographic quantum error correction systems. Some believe holographic quantum error correction provides essential mechanisms for holographic correspondence, consistency based on quantum mechanical information conservation requirements and mathematical quantum error correction theory, while others suggest that holographic correspondence operates through alternative information preservation mechanisms that transcend conventional quantum error correction frameworks. The role of quantum error correction in holographic physics continues to be investigated as quantum information theory advances and holographic correspondence understanding develops. Fault-tolerant holographic computation investigates whether holographic systems can perform quantum computation while maintaining error correction protection. Holographic quantum computing potentially achieving fault-tolerant quantum computation through boundary quantum information processing protected by holographic error correction mechanisms. These fault-tolerant scenarios provide frameworks for understanding holographic computational capabilities while connecting holographic physics to quantum computation through error correction, protected quantum information processing. Holographic error correction experimental analogues utilize laboratory quantum systems to investigate quantum error correction mechanisms that parallel holographic correspondence. Experimental quantum error correction providing observational tests for holographic protection mechanisms while creating laboratory demonstrations of distributed quantum information protection. These experimental approaches provide empirical validation of holographic error correction principles while establishing practical quantum error correction techniques inspired by holographic correspondence mechanisms. The irony of holographic quantum protection lies in its preservation of quantum information through dimensional reduction that appears to eliminate information storage capacity. Holographic error correction maintaining complete quantum information despite boundary encoding that seems insufficient for bulk information storage. Quantum error correction transcending apparent dimensional limitations through quantum mechanical protection mechanisms that preserve information coherence despite holographic dimensional compression. Quantum protection creating information preservation through boundary encoding, while bulk space-time appears to contain information that exceeds boundary storage capacity. Holographic error correction resolving apparent information storage paradox through quantum mechanical information protection that transcends classical information storage limitations while maintaining holographic correspondence consistency. Tensor networks demonstrate geometric emergence through mathematical structures that reproduce gravitational physics using quantum entanglement patterns. Tensor network models creating effective space-time geometry through network connectivity while establishing computational frameworks for understanding how geometric relationships emerge from quantum information processing. These mathematical network structures provide explicit constructions showing how quantum entanglement naturally generates gravitational phenomena, including space-time curvature, black hole formation, and cosmological evolution through network geometry rather than fundamental geometric space-time properties. Mirror tensor networks create hierarchical geometric structures through multi-scale entanglement renormalization that generates effective gravitational dynamics at different length scales. Mirror architecture, demonstrating how quantum entanglement networks naturally incorporate geometric scaling relationships that reproduce general relativistic gravitational physics. These hierarchical networks provide computational models for space-time emergence, while revealing how quantum entanglement organization creates effective geometric properties through scale-dependent network connectivity patterns. ADS, CFT tensor network applications utilize tensor network mathematical frameworks to model holographic correspondence. Tensor networks providing computational tools for understanding boundary bulk correspondence through network connectivity that creates geometric emergence within holographic duality relationships. These tensor network holographic models establish practical computational approaches for holographic correspondence while demonstrating how tensor network mathematics naturally generates both boundary quantum field theory and bulk gravitational physics through unified network structures. Quantum error correction integration within tensor networks creates geometric emergence that includes information protection mechanisms, tensor network quantum codes generating effective space-time geometry while maintaining quantum information protection through network redundancy and error correction capabilities. These error correction tensor networks demonstrate how geometric emergence naturally incorporates quantum information protection, while providing robust computational frameworks for understanding protected geometric emergence through quantum error correction mechanisms. Random tensor network models investigate geometric emergence properties that remain universal across different network architectures. Random networks exhibiting geometric emergence characteristics that transcend specific network construction details while revealing universal principles governing quantum entanglement-based geometric emergence. These random network studies provide statistical frameworks for understanding geometric emergence while establishing universal properties of quantum entanglement networks that generate effective gravitational physics. Entanglement renormalization techniques within tensor networks create coarse graining procedures that generate effective geometric descriptions at different length scales. Renormalization group flows in tensor networks, producing emergent gravitational dynamics through systematic entanglement reduction and network simplification. These renormalization approaches provide computational tools for multi-scale geometric emergence, while demonstrating how quantum entanglement naturally generates effective gravitational theories through systematic coarse graining procedures. Tensor network simulations of black hole physics demonstrate how network connectivity modifications reproduce black hole formation, evolution, and information processing. Tensor network black holes exhibiting thermodynamic properties and information preservation mechanisms that parallel gravitational black hole physics through network dynamics. These black hole simulations provide computational models for black hole physics while revealing how tensor networks naturally generate gravitational phenomena, including black hole thermodynamics and information processing through network connectivity patterns. Holographic entanglement entropy calculations using tensor networks provide computational tools for understanding entanglement geometry relationships. Tensor network entropy calculations reproducing holographic entanglement entropy formulas through network-based geometric constructions. These entropy calculations establish computational frameworks for holographic entanglement while demonstrating how tensor networks naturally generate geometric interpretations for quantum entanglement through network connectivity and information processing capabilities. Tensor network cosmology models investigate whether cosmic evolution can be reproduced through tensor network dynamics. Cosmic structure formation and cosmic expansion potentially emerging from tensor network evolution rather than fundamental cosmic gravitational dynamics. These cosmological applications provide frameworks for understanding cosmic evolution through quantum entanglement networks, while extending tensor network geometric emergence to cosmic scale physics through network evolution processes. Quantum simulation applications utilize tensor networks to create laboratory analogues of geometric emergence. Experimental tensor network implementations providing observational tests for quantum entanglement-based geometric emergence while creating controllable quantum systems that exhibit holographic correspondence properties. These experimental approaches provide empirical validation of tensor network geometric emergence, while establishing practical quantum simulation techniques for investigating holographic physics principles. Machine learning applications to tensor networks investigate whether artificial intelligence techniques can optimize tensor network architectures for geometric emergence. Machine learning optimization potentially improving tensor network efficiency while revealing optimal network structures for gravitational physics reproduction through automated network design. These machine learning approaches provide computational tools for tensor network optimization while creating connections between artificial intelligence and quantum gravity through geometric emergence optimization. Some believe tensor networks provide definitive computational proof of geometric emergence from quantum entanglement based on explicit mathematical constructions and computational simulations, while others suggest that tensor network geometric emergence represents mathematical artifacts that may not correspond to physical space-time emergence despite computational success. The physical significance of tensor network geometric emergence continues to be investigated as computational techniques advance and experimental validation improves. Continuous tensor networks investigate geometric emergence in continuum limits, where discrete network structures approach continuous space-time descriptions. Continuum tensor networks providing mathematical bridges between discrete quantum information processing and continuous gravitational physics through limiting procedures. These continuum approaches establish connections between discrete network geometric emergence and continuous space-time physics, while revealing how quantum entanglement networks naturally generate continuous geometric descriptions through appropriate mathematical limits. Tensor network quantum field theory applications demonstrate how network structures generate quantum field theoretical dynamics, including particle creation, field propagation, and interaction phenomena. Tensor network field theory providing computational frameworks for understanding quantum field emergence from quantum entanglement networks. These field theory applications extend tensor network geometric emergence to include matter field dynamics, while creating unified frameworks for understanding both geometric and matter emergence from quantum entanglement through network-based quantum information processing. The irony of tensor network geometric emergence lies in its demonstration of space-time geometry arising from discrete network structures that appear fundamentally non-geometric. Quantum entanglement networks generating convincing geometric space-time physics while operating through discrete network connectivity that transcends geometric description. Mathematical tensor networks creating effective gravitational dynamics through quantum information processing that remains fundamentally different from geometric space-time physics despite reproducing gravitational phenomena. Network-based geometric emergence revealing space-time geometry as emergent mathematical construction rather than fundamental physical reality, while creating computational frameworks that successfully reproduce all observed gravitational physics through discrete quantum entanglement network dynamics. Cosmic microwave background holographic signatures emerge from temperature fluctuation patterns and polarization characteristics that could preserve evidence of boundary information processing during cosmic inflation. Cosmic background radiation potentially encoding information about holographic cosmic evolution through statistical patterns that reflect boundary quantum field theory dynamics rather than bulk three-dimensional cosmic physics. These cosmic background signatures provide observational windows into potential cosmic holographic processes while establishing empirical frameworks for testing cosmic boundary information processing scenarios through precision cosmic microwave background analysis and statistical pattern recognition techniques. Temperature fluctuation statistics in cosmic microwave background exhibit specific correlation patterns that could result from cosmic boundary quantum field theory rather than three-dimensional cosmic structure formation. Fluctuation characteristics potentially reflecting boundary information processing constraints and boundary quantum field dynamics that generate cosmic structure through holographic projection. These statistical signatures provide quantitative tests for cosmic holographic scenarios while revealing cosmic background radiation characteristics that transcend conventional three-dimensional cosmic inflation predictions through boundary-based cosmic evolution mechanisms. Polarization patterns in cosmic microwave background create additional observational signatures that could reveal cosmic boundary information processing effects. Polarization characteristics potentially encoding information about cosmic boundary quantum field theory, evolution during cosmic inflation, and early cosmic structure formation. These polarization studies provide complementary observational constraints on cosmic holographic scenarios, while establishing additional empirical tests for boundary-based cosmic evolution through an electromagnetic polarization analysis that transcends temperature fluctuation studies. Cosmic background radiation isotropy characteristics exhibit remarkable uniformity that could result from cosmic boundary information processing rather than causal horizon limitations in three-dimensional cosmic expansion. Cosmic isotropy potentially reflecting boundary quantum field theory, equilibration rather than causal connectivity constraints within three-dimensional cosmic spacetime. These isotropy observations provide observational constraints on cosmic holographic scenarios while revealing cosmic background characteristics that transcend conventional cosmic inflation horizon problem solutions through boundary information processing mechanisms. Non-Gaussianity searches in cosmic microwave background investigate deviations from Gaussian statistical patterns that could reveal cosmic boundary information processing signatures. Non-Gaussian fluctuation patterns potentially indicating boundary quantum field theory, dynamics that transcend conventional cosmic inflation predictions for Gaussian fluctuation generation. These non-Gaussianity studies provide observational tests for cosmic boundary evolution while establishing statistical frameworks for detecting boundary information processing effects through cosmic background radiation statistical analysis techniques. Cosmic microwave background anomalies, including large-scale temperature asymmetries and unusual correlation patterns, could indicate cosmic boundary information processing effects that create observational signatures transcending conventional cosmic evolution predictions. Cosmic anomalies, potentially reflecting boundary quantum field theory dynamics, rather than statistical fluctuations within three-dimensional cosmic evolution. These anomaly investigations provide observational frameworks for cosmic holographic detection, while revealing cosmic background characteristics that challenge conventional cosmic evolution scenarios through boundary-based cosmic dynamics. Planck's satellite precision measurements achieve observational accuracy sufficient for detecting subtle cosmic boundary information processing signatures. Cosmic microwave background precision observations providing empirical constraints on cosmic holographic scenarios, while establishing measurement capabilities for testing boundary-based cosmic evolution predictions. These precision measurements create observational opportunities for cosmic holographic detection, while providing quantitative frameworks for comparing cosmic boundary evolution scenarios with observational cosmic background radiation characteristics. Cosmic background radiation spectral distortions investigate deviations from black-body thermal characteristics that could indicate cosmic boundary information processing effects. Spectral distortion signatures potentially revealing boundary quantum field theory, thermal evolution that transcends conventional cosmic thermal equilibration mechanisms. These spectral studies provide additional observational tests for cosmic boundary scenarios, while establishing thermal analysis frameworks for detecting boundary information processing effects through cosmic background radiation spectroscopic analysis. Cross-correlation analysis between cosmic microwave background and large-scale structure observations could reveal cosmic boundary information processing signatures that create correlated cosmic evolution patterns. Boundary-based cosmic evolution potentially generating cosmic structure correlations that transcend conventional gravitational structure formation predictions. These correlation studies provide observational frameworks for testing cosmic boundary evolution, while establishing statistical analysis techniques for detecting boundary information processing effects through multi-wavelength cosmic observations. Cosmic microwave background lensing effects create gravitational distortion patterns that could reveal cosmic boundary information, processing influences on cosmic structure formation, lensing signatures potentially indicating boundary-based cosmic evolution that affects cosmic structure development through holographic projection mechanisms. These lensing studies provide gravitational observational tests for cosmic boundary scenarios while establishing gravitational analysis frameworks for detecting boundary information processing effects through cosmic background radiation, gravitational distortion analysis. Future cosmic microwave background observations, including space-based polarization missions and ground-based interferometric arrays, could achieve observational sensitivity sufficient for definitive cosmic boundary information processing detection. Future observations providing enhanced empirical tests for cosmic holographic scenarios while establishing next-generation observational capabilities for cosmic boundary evolution investigation. These future observational programs create prospects for cosmic holographic confirmation while providing technological frameworks for advancing cosmic boundary information processing detection capabilities. Some believe cosmic microwave background observations provide compelling evidence for cosmic boundary information processing based on statistical analysis of cosmic background radiation characteristics and cosmic structure correlation patterns, while others suggest that cosmic background observations remain consistent with conventional three-dimensional cosmic evolution, despite statistical patterns that could indicate boundary effects. The interpretation of cosmic microwave background evidence for cosmic holographic evolution continues to evolve as observational precision improves and statistical analysis techniques advance. Cosmic microwave background foreground contamination effects require careful analysis to distinguish genuine cosmic boundary signatures from astrophysical foreground emissions, foreground removal techniques providing observational frameworks for isolating cosmic boundary information processing signatures, while establishing analysis procedures for cosmic holographic detection through contamination mitigation. These foreground studies create observational requirements for cosmic boundary detection, while providing analytical frameworks for cosmic holographic signature identification through systematic foreground analysis. Machine learning applications to cosmic microwave background analysis utilize artificial intelligence techniques to identify subtle cosmic boundary information processing signatures. Machine learning pattern recognition potentially detecting cosmic holographic signatures that transcend conventional statistical analysis capabilities while providing automated analysis frameworks for cosmic boundary evolution investigation. These machine learning approaches create computational tools for cosmic holographic detection while establishing artificial intelligence frameworks for cosmic boundary signature recognition through automated pattern analysis. The irony of cosmic microwave background holographic evidence lies in its preservation of cosmic boundary information processing signatures within observational data that appears to document three-dimensional cosmic evolution. Cosmic background radiation potentially encoding boundary quantum field theory, evolution, while appearing to preserve information about bulk three-dimensional cosmic physics. Holographic cosmic evolution signatures hiding within cosmic microwave background observations that seem to confirm conventional cosmic evolution, despite potentially reflecting boundary information processing dynamics that generated cosmic background radiation through holographic projection, rather than three-dimensional cosmic thermal evolution. Cosmic boundary signatures concealed within cosmic background observations through holographic encoding that creates cosmic thermal illusion, masking underlying boundary information processing origins. Dark matter emerges as holographic shadow effects that manifest apparent invisible matter distributions through boundary information processing artifacts, rather than fundamental dark matter particle populations within cosmic three-dimensional volumes. Gravitational effects attributed to dark matter potentially arising from cosmic boundary encoding mechanisms that create apparent matter through holographic projection. These holographic dark matter scenarios eliminate requirements for exotic matter particles, while explaining dark matter gravitational effects through cosmic boundary information processing that generates apparent matter distributions through dimensional projection rather than physical matter particles distributed throughout cosmic space-time. Galaxy rotation curve anomalies reveal gravitational effects that exceed visible matter contributions by substantial factors. Galactic dynamics requiring additional gravitational sources that remain electromagnetically invisible while providing gravitational influence consistent with extended matter distributions surrounding galactic structures. These rotation curve measurements could reflect holographic boundary effects that create apparent matter distributions through cosmic boundary information processing rather than requiring exotic dark matter particles. Boundary gravitational effects generating apparent matter through holographic projection mechanisms. Gravitational lensing observations detect matter concentrations through space-time curvature effects that bend electromagnetic radiation paths. Lensing measurements revealing mass distributions that exceed visible matter estimates, while creating gravitational lens effects consistent with extended invisible matter distributions. These lensing effects could represent holographic boundary information processing artifacts that create apparent matter concentrations through boundary encoding, rather than fundamental matter distributions within observed cosmic regions. Large-scale structure formation simulations require substantial dark matter contributions to cosmic mass budget for consistency with observed galaxy and galaxy cluster distributions. N-body gravitational simulations demonstrating that visible matter alone cannot account for cosmic structure development through gravitational instability growth over cosmic evolution timescales. These structure formation requirements could reflect cosmic boundary information processing effects that generate apparent cosmic structure through holographic projection, rather than requiring exotic dark matter particles for cosmic structure formation. Cosmic microwave background acoustic oscillations encode information about cosmic matter distributions through baryon photon fluid dynamics. Acoustic peak analysis revealing matter density parameters that require substantial invisible matter contributions to cosmic mass energy budget for consistency with observed acoustic oscillation patterns. These acoustic measurements could reflect cosmic boundary information processing signatures that create apparent matter density through boundary encoding, rather than fundamental cosmic matter distributions. Holographic dark matter models propose that apparent dark matter effects result from boundary information processing that creates gravitational signatures without requiring fundamental dark matter particles. Cosmic boundary encoding generating apparent matter distributions through holographic projection mechanisms that transcend conventional matter-particle scenarios. These holographic models provide alternative explanations for dark matter observations while eliminating exotic matter particle requirements through cosmic boundary information processing effects. Modified gravity theories attempt to explain dark matter effects through gravitational field modifications rather than exotic matter particles. Alternative gravity models demonstrating how gravitational physics changes could account for galactic rotation curves and cosmic structure formation without requiring dark matter particles. These modified gravity approaches could reflect holographic boundary effects that modify apparent gravitational physics through boundary information processing, rather than requiring fundamental gravitational field modifications. Cosmic void characteristics reveal large-scale cosmic structure patterns where apparent dark matter influences create complex density distributions, including underdense regions that span hundreds of megaparsecs. Void statistics providing observational constraints on dark matter clustering properties while revealing cosmic structure patterns that could reflect boundary information processing effects. These void observations could indicate cosmic boundary encoding effects that create apparent cosmic structure through holographic projection rather than fundamental matter distribution patterns. Dark matter direct detection experiments search for exotic matter, particle interactions through underground detector systems, experimental programs investigating supersymmetric particles and other exotic matter candidates through direct detection techniques that have yielded null results despite increasingly sensitive searches. These null detection results remain consistent with holographic dark matter scenarios where apparent dark matter effects result from boundary information processing rather than fundamental exotic matter particles that could be detected through direct interaction experiments. Primordial black hole dark matter scenarios investigate whether dark matter consists of black hole populations formed during early cosmic epochs. Primordial black holes potentially providing dark matter contributions through gravitational effects, rather than exotic matter particles. These black hole scenarios could reflect cosmic boundary information processing effects that create apparent black hole populations through boundary encoding, rather than fundamental primordial black hole formation during early cosmic evolution. Axion dark matter models propose that dark matter consists of extremely light particles that remain electromagnetically invisible while providing gravitational effects through coherent field oscillations. Axion scenarios attempting to explain dark matter through specific exotic particle physics rather than holographic boundary effects. These axion models represent conventional dark matter particle approaches that contrast with holographic dark matter scenarios, where apparent dark matter effects result from boundary information processing rather than fundamental axion particles. Some believe dark matter represents fundamental exotic matter particles based on gravitational evidence and cosmic structure formation requirements, despite null direct detection results, while others suggest that dark matter effects could result from holographic boundary information processing or modified gravitational physics that transcends conventional matter particle explanations. The nature of dark matter continues to be investigated as detection experiments improve sensitivity and theoretical understanding of holographic physics advances. Sterile neutrino dark matter scenarios propose that dark matter consists of right-handed neutrinos that remain electromagnetically invisible while providing gravitational effects through weak interaction physics. Sterile neutrino models attempting to explain dark matter through extensions to standard model particle physics. These neutrino scenarios represent additional conventional dark matter particle approaches that provide alternatives to holographic dark matter explanations through fundamental particle physics extensions. Dark matter self-interaction models investigate whether dark matter particles exhibit self-interaction properties that could explain observed dark matter distribution characteristics. Self-interacting dark matter potentially resolving discrepancies between dark matter simulations and observational dark matter distributions through particle self-interaction physics. These self-interaction models represent refinements to conventional dark matter particle scenarios that contrast with holographic dark matter approaches where apparent dark matter effects result from boundary information processing. The irony of holographic dark matter shadows lies in their creation of convincing matter effects without fundamental matter particles. Apparent dark matter distributions emerging from cosmic boundary information processing while appearing to represent physical matter particles distributed throughout cosmic volumes. Holographic dark matter effects generating gravitational signatures that seem to require exotic matter particles, while actually resulting from boundary encoding mechanisms that create matter illusion through holographic projection. Cosmic boundary information processing creating dark matter gravitational effects that convince observational astronomy of exotic matter particle existence, despite holographic origins that transcend fundamental matter particle requirements through boundary information processing, artifacts that generate apparent matter through dimensional projection mechanisms. Quantum gravity emerges through holographic duality mechanisms that generate gravitational phenomena from boundary quantum field theory rather than bulk space-time quantization. Holographic approaches providing alternative frameworks for quantum gravity where gravitational effects arise from boundary quantum information processing rather than fundamental quantum gravitational field interactions within three-dimensional space-time. These holographic quantum gravity scenarios eliminate requirements for space-time quantization while generating gravitational phenomena through boundary quantum field theory dynamics that transcend conventional quantum gravity, approaches requiring space-time discretization at Planck scales. Loop quantum gravity investigations into space-time discretization create quantum geometric structures through fundamental space-time quantization. Loop quantum gravity proposing that space-time exhibits discrete geometric properties at Planck scales rather than smooth continuous manifold characteristics. These discrete space-time approaches contrast with holographic quantum gravity scenarios where gravitational phenomena emerge from boundary quantum field theory without requiring bulk space-time quantization. holographic quantum gravity transcending space-time discretization through boundary information processing mechanisms. String theory applications to quantum gravity provide microscopic foundations for gravitational physics through fundamental string dynamics that naturally incorporate both quantum mechanics and general relativity. String-theoretical quantum gravity operating through string perturbation theory and non-perturbative string dynamics that unify gravitational and quantum mechanical phenomena. These string-theoretical approaches could reflect holographic quantum gravity mechanisms where string dynamics generate both boundary quantum field theory and bulk gravitational physics through holographic correspondence rather than fundamental string interactions within bulk spacetime. Causal dynamical triangulations create discrete spacetime models through random geometric constructions that sum over possible spacetime geometries. Causal triangulation approaches investigating quantum gravity through path integral methods that integrate over discrete geometric configurations rather than continuous spacetime manifolds. These discrete geometry approaches provide alternative frameworks for quantum gravity that could incorporate holographic principles through boundary bulk correspondence within discrete geometric models, rather than requiring fundamental bulk space-time quantization. Emergent gravity theories propose that gravitational phenomena emerge from more fundamental quantum information processing mechanisms, rather than representing fundamental geometric space-time properties. Emergent gravity potentially explaining gravitational physics through quantum entanglement and quantum information thermodynamics that transcend classical gravitational field theory. These emergent approaches align with holographic quantum gravity scenarios where gravitational phenomena result from boundary quantum information processing rather than fundamental bulk gravitational field quantization. Black hole quantum gravity applications investigate quantum mechanical effects within black hole physics, including Hawking radiation, black hole thermodynamics, and information preservation mechanisms that require quantum gravitational understanding for complete theoretical description. These black hole quantum effects could reflect holographic quantum gravity, where black hole physics emerges from boundary quantum field theory, rather than bulk quantum gravitational processes. Holographic black hole physics operating through boundary information processing, rather than quantum gravitational dynamics within black hole interiors. Cosmological quantum gravity scenarios explore quantum mechanical effects during early cosmic epochs, including cosmic inflation, cosmic structure formation, and cosmic evolution processes that require quantum gravitational understanding for theoretical completion. These cosmological applications could utilize holographic quantum gravity, where cosmic evolution emerges from cosmic boundary quantum field theory, rather than bulk cosmic quantum gravitational dynamics. Holographic cosmology operating through boundary information processing rather than quantum gravitational processes within cosmic bulk spacetime. Quantum gravity phenomenology investigates observational signatures of quantum gravitational effects that could provide empirical tests for quantum gravity theories. Observational quantum gravity requiring experimental verification of quantum gravitational predictions through astronomical observations and laboratory experiments. These phenomenological approaches could test holographic quantum gravity scenarios, where quantum gravitational signatures emerge from boundary quantum field theory, rather than bulk space-time quantum effects. Holographic quantum gravity providing alternative predictions for quantum gravitational observational signatures. Holographic renormalization techniques address mathematical divergences in holographic quantum gravity calculations through systematic regularization procedures that extract finite physical predictions from boundary quantum field theory. Holographic renormalization providing mathematical tools for practical quantum gravity calculations while maintaining consistency between boundary field theory and bulk gravitational physics. These renormalization frameworks establish computational approaches for holographic quantum gravity while creating mathematical tools for quantum gravitational calculations through boundary field theory methods. Quantum gravity unification attempts investigate whether quantum gravity provides unified descriptions of all fundamental physical interactions, including electromagnetic, weak nuclear and strong nuclear forces through quantum gravitational frameworks that incorporate particle physics within gravitational theoretical structures. These unification scenarios could utilize holographic quantum gravity, where all fundamental interactions emerge from boundary quantum field theory, rather than bulk space-time field interactions. Holographic unification providing alternative frameworks for fundamental physics unification through boundary information processing. ADS/CFT quantum gravity applications demonstrate specific examples of holographic quantum gravity through anti-de Sitter space-time correspondence to conformal field theory. ADS/CFT providing mathematical tools for quantum gravity calculations through established holographic correspondence relationships that connect gravitational physics to boundary quantum field theory. These ADS/CFT applications establish practical frameworks for holographic quantum gravity while providing computational tools for quantum gravitational calculations through boundary field theory methods. Some believe holographic quantum gravity provides compelling approaches to quantum gravity unification based on holographic correspondence success and boundary quantum field theory consistency, while others suggest that quantum gravity requires fundamental bulk space-time quantization despite holographic correspondence mathematical elegance. The viability of holographic quantum gravity continues to be investigated as holographic theory develops and quantum gravity understanding advances through theoretical development and observational constraint improvement. Quantum gravity experimental tests utilize precision measurements of gravitational phenomena that could reveal quantum gravitational effects. Experimental quantum gravity investigating deviations from classical gravitational predictions through high-precision gravitational measurements and quantum mechanical gravitational effect detection. These experimental approaches could test holographic quantum gravity predictions, where quantum gravitational signatures emerge from boundary quantum field theory rather than bulk space-time quantum effects. Holographic quantum gravity providing alternative experimental predictions for quantum gravitational phenomena detection. Quantum gravity information theory. Applications investigate connections between quantum gravity and quantum information science. Quantum gravitational information processing potentially operating through quantum information theoretical mechanisms that transcend classical gravitational information processing. These information theoretical approaches align with holographic quantum gravity, where gravitational phenomena emerge from boundary quantum information processing rather than bulk space-time quantum gravitational dynamics. Holographic quantum gravity naturally incorporating quantum information theoretical foundations. The irony of holographic quantum gravity lies in its resolution of quantum gravity through dimensional reduction that eliminates gravitational quantization requirements. Holographic quantum gravity solving quantum gravity problems by removing gravity from quantum gravity through boundary emergence mechanisms. Quantum gravitational unification achieved through holographic correspondence that transcends quantum gravitational quantization by generating gravitational phenomena from boundary quantum field theory rather than quantum gravitational field interactions. Holographic quantum gravity creating quantum gravitational physics without quantum gravity through boundary information processing that eliminates quantum space-time quantization while reproducing all quantum gravitational phenomena through boundary quantum field theory, dynamics that transcend fundamental quantum gravitational field requirements. Information paradox holographic resolution operates through boundary encoding mechanisms that preserve quantum information despite apparent bulk information destruction during gravitational collapse and black hole evaporation. Holographic information preservation maintaining quantum mechanical unitarity through boundary quantum field theory, while resolving fundamental conflicts between quantum mechanics and general relativity. These holographic resolution mechanisms demonstrate how boundary information processing transcends bulk information destruction, while preserving quantum information through dimensional reduction that maintains complete information content despite apparent information loss during gravitational processes. Black hole information destruction scenarios arise when quantum field theory calculations suggest that Hawking radiation carries insufficient information to preserve quantum states of matter that falls into black holes. Thermal radiation characteristics indicating information scrambling that violates quantum mechanical reversibility principles and creates fundamental tensions between quantum mechanics and gravitational physics. These information destruction challenges motivate holographic solutions where boundary encoding preserves quantum information through holographic correspondence mechanisms that transcend apparent bulk information loss. Quantum mechanical unitarity requirements demand that quantum information remains conserved during all physical processes, including gravitational collapse and black hole formation. Quantum mechanics requiring reversible evolution that preserves information content despite classical gravitational predictions for information destruction within black hole interiors. These unitarity constraints create fundamental challenges for gravitational physics while motivating holographic information preservation mechanisms that maintain quantum mechanical consistency through boundary information processing. Holographic information storage operates through boundary quantum field theory, encoding that preserves complete bulk information content within boundary degrees of freedom. Holographic encoding demonstrating how boundary information processing can maintain complete information preservation despite dimensional reduction from bulk to boundary systems. These holographic storage mechanisms provide theoretical frameworks for information preservation, while revealing how boundary encoding transcends classical information storage limitations through quantum mechanical information processing capabilities. ADS CFT information preservation demonstrates specific examples of holographic information conservation through anti-de Sitter space-time correspondence to conformal field theory. ADS-CFT duality, providing mathematical frameworks for information preservation where bulk gravitational information corresponds exactly to boundary field theory information content. These ADS/CFT examples establish practical demonstrations of holographic information preservation while creating computational tools for information conservation analysis through boundary bulk correspondence calculations. Quantum error correction applications to information paradox resolution utilize quantum mechanical error correction principles to understand how boundary quantum field theory preserves information despite bulk gravitational perturbations and environmental decoherence effects. Quantum error correction providing protection mechanisms for holographic information preservation. These error correction frameworks demonstrate how quantum mechanical protection naturally emerges within holographic correspondence, while establishing theoretical foundations for robust information preservation through quantum mechanical protection systems. Black hole complementarity proposals attempt to resolve information paradox through observer-dependent descriptions, where infalling observers experience smooth horizon crossing while external observers witness information preservation through boundary encoding. Complementarity suggesting that information destruction and information preservation represent perspective-dependent descriptions of identical physical processes. These complementarity scenarios provide alternative approaches to information paradox resolution, while maintaining consistency with both quantum mechanics and general relativity through observer-dependent physical descriptions. Firewall paradox complications arise when quantum field theory predicts high-energy radiation near black hole horizons that could destroy infalling matter while maintaining quantum mechanical consistency. Firewall scenarios creating additional challenges for information preservation while revealing tensions between different approaches to quantum mechanical information conservation near gravitational boundaries. These firewall challenges motivate holographic solutions where boundary information processing transcends firewall effects through dimensional reduction mechanisms. Entanglement-based information preservation mechanisms operate through quantum entanglement networks that maintain information correlation despite apparent spatial separation. Quantum entanglement potentially preserving information through non-local correlation that transcends classical information transmission limitations. These entanglement mechanisms provide quantum mechanical foundations for information preservation, while creating connections between information conservation and quantum entanglement dynamics that could support holographic information preservation. Cosmic information paradox extensions investigate whether information conservation requirements apply to cosmic evolution and cosmic structure formation. Cosmic information content potentially requiring preservation mechanisms that maintain quantum information despite cosmic expansion and cosmic gravitational evolution. These cosmic information challenges provide broader contexts for information paradox problems while extending holographic information preservation principles to cosmic-scale information processing systems through cosmic boundary encoding mechanisms. String theory. Information preservation applications utilize string theoretical frameworks to understand information conservation during gravitational processes. String theory potentially providing microscopic mechanisms for information preservation through fundamental string dynamics that maintain information content despite gravitational collapse and black hole formation. These string theoretical approaches provide microscopic foundations for information preservation, while creating connections between information conservation and fundamental string theoretical physics. Some believe holographic information preservation provides compelling resolution to information paradox problems based on boundary encoding mechanisms and quantum mechanical information conservation requirements, while others suggest that information paradox resolution requires alternative approaches that transcend holographic correspondence despite mathematical elegance of boundary information preservation. The effectiveness of holographic information paradox resolution continues to be investigated as holographic theory develops and quantum gravity understanding advances. Holographic information reconstruction mechanisms investigate how boundary information encoding enables complete bulk information recovery. Holographic reconstruction demonstrating how boundary quantum field theory contains sufficient information for complete bulk system description despite dimensional reduction. These reconstruction mechanisms provide practical frameworks for holographic information recovery, while revealing how boundary encoding maintains complete information accessibility through appropriate boundary information processing techniques. Information preservation experimental tests utilize quantum mechanical systems to investigate information conservation principles that parallel gravitational information preservation. Experimental quantum information providing observational validation of information conservation mechanisms, while creating laboratory analogues for gravitational information preservation scenarios. These experimental approaches provide empirical support for information conservation principles, while establishing practical quantum information techniques that could validate holographic information preservation mechanisms. The irony of holographic information paradox resolution lies in its preservation of information through apparent information elimination. Holographic information conservation maintaining complete quantum information through dimensional reduction that seems to eliminate information storage capacity. Boundary encoding, preserving complete bulk information despite boundary storage limitations that appear insufficient for complete information preservation. Holographic information preservation transcending classical information storage constraints through quantum mechanical information processing that maintains complete information content despite dimensional compression. Information paradox resolution achieved through holographic mechanisms that preserve information by eliminating information storage requirements while maintaining complete information accessibility through boundary quantum field theory, processing that transcends bulk information storage limitations. Cosmic evolution represents computation occurring on cosmic boundary surfaces where universe development emerges from boundary quantum information processing rather than bulk three-dimensional cosmic physics. Cosmic structure formation and cosmic expansion, potentially operating through cosmic boundary computational mechanisms that transcend conventional cosmic gravitational dynamics. These cosmic computation scenarios suggest that observable cosmic evolution reflects computational processes operating on cosmic horizon boundaries. Cosmic history emerging from cosmic boundary information processing that generates cosmic structure through computational rather than gravitational mechanisms. Computational complexity measures for cosmic evolution investigate whether cosmic structure formation requires computational resources that exceed classical computation capabilities. Cosmic development potentially demanding quantum computational mechanisms that transcend classical computational limitations through quantum information processing operating on cosmic boundaries. These complexity analyses provide theoretical frameworks for understanding cosmic evolution as a computational process, while revealing computational requirements for cosmic structure formation and cosmic biological evolution through boundary computational mechanisms. Cosmic information processing rates determine computational capabilities of cosmic boundary systems for generating cosmic structure and cosmic evolution. Cosmic computation operating at information processing speeds that depend on cosmic boundary information density and quantum computational efficiency. These processing rate calculations establish computational constraints on cosmic evolution while revealing computational capabilities of cosmic boundary systems for cosmic structure formation through quantum information processing mechanisms that operate at cosmic boundary surfaces. Digital physics applications to cosmic evolution investigate whether cosmic physics operates according to computational principles, where physical laws represent computational algorithms rather than continuous mathematical equations. Digital cosmic physics potentially operating through discrete computational processes that generate apparent continuous cosmic evolution through computational approximation. These digital physics scenarios provide frameworks for understanding cosmic evolution as computational simulation, while connecting cosmic physics to computational science through discrete information processing mechanisms. Cellular automata cosmic models demonstrate how simple computational rules can generate complex cosmic structure patterns through iterative computational processes. Cellular automaton cosmic evolution creating cosmic structure emergence through discrete computational steps that reproduce cosmic evolution characteristics through rule-based computational mechanisms. These cellular automaton models provide computational frameworks for cosmic evolution, while revealing how simple computational algorithms can generate complex cosmic structure through emergent computational behavior. Quantum computational cosmic evolution scenarios investigate whether cosmic development utilizes quantum computational mechanisms that transcend classical computational limitations. Cosmic quantum computation potentially achieving computational capabilities that exceed classical cosmic computation through quantum superposition and quantum entanglement effects. These quantum computational frameworks provide theoretical approaches for understanding cosmic evolution through quantum information processing, while revealing quantum computational advantages for cosmic structure formation and cosmic biological evolution. Cosmic simulation hypothesis considerations explore whether observable cosmic reality represents computational simulation operating within higher-level computational systems. Cosmic simulation potentially explaining cosmic fine-tuning and cosmic evolution through computational optimization rather than physical evolutionary processes. These simulation scenarios provide alternative frameworks for cosmic evolution, while connecting cosmic physics to computational science through simulation theory that transcends conventional cosmic physics interpretations. Algorithmic information theory applications to cosmic evolution investigate whether cosmic structure formation operates according to algorithmic compression principles, where cosmic complexity emerges from simple computational algorithms. Cosmic algorithmic complexity potentially revealing computational foundations for cosmic evolution through information theoretical analysis of cosmic structure. These algorithmic approaches provide information theoretical frameworks for cosmic evolution, while revealing computational characteristics of cosmic structure formation through algorithmic compression and computational complexity analysis. Cosmic Turing machine scenarios investigate whether cosmic evolution operates according to universal computation principles, where cosmic physics represents computational processes operating on cosmic scale computational architectures. Cosmic Turing machines potentially providing universal computational frameworks for cosmic evolution that transcend specific computational implementations. These universal computation scenarios provide theoretical frameworks for cosmic computation, while revealing computational universality principles that could govern cosmic evolution through boundary computational mechanisms. Holographic computational correspondence demonstrates how boundary quantum computation generates bulk gravitational dynamics through computational holographic mechanisms. Holographic computation creating gravitational phenomena through boundary information processing that operates according to computational rather than geometric principles. These holographic computational frameworks provide computational interpretations for holographic correspondence, while revealing how gravitational physics emerges from computational processes operating on boundary surfaces. Cosmic consciousness computational emergence investigates whether conscious experience emerges from cosmic boundary computational processes rather than local biological neural computation. Cosmic computation potentially generating consciousness through boundary information processing that transcends local biological computational limitations. These consciousness computational scenarios provide frameworks for understanding consciousness through cosmic computation, while connecting consciousness emergence to cosmic boundary information processing through computational rather than biological mechanisms. Some believe cosmic evolution operates through computational mechanisms based on information theoretical analysis and computational cosmic modeling, while others suggest that cosmic physics operates through continuous mathematical principles that transcend discrete computational approximation despite computational modeling success. The computational nature of cosmic evolution continues to be investigated as computational science advances and cosmic evolution understanding develops through theoretical and observational progress. Cosmic computational optimization investigates whether cosmic evolution operates according to optimization principles, where cosmic development maximizes computational efficiency or computational output. Cosmic optimization potentially explaining cosmic fine-tuning through computational optimization, rather than anthropic selection or multiverse parameter variation. These optimization scenarios provide computational explanations for cosmic parameter precision, while revealing computational objectives that could govern cosmic evolution through boundary computational optimization processes. Emergent computation in cosmic systems explores how complex computational behavior emerges from simple cosmic physical processes. Cosmic emergence potentially generating computational capabilities that transcend individual cosmic component computational limitations through collective computational behavior. These emergent scenarios provide frameworks for understanding cosmic computational capabilities while revealing how cosmic computation emerges from cosmic physical dynamics through collective computational behavior that transcends individual cosmic system computational limitations. The irony of cosmic computational evolution lies in its suggestion that cosmic reality represents computational process rather than physical evolution. Cosmic structure formation and cosmic biological evolution potentially emerging from cosmic boundary computation while appearing to operate through physical cosmic processes. Cosmic computation creating cosmic physical illusion through computational simulation that generates convincing cosmic physics while operating through computational rather than physical mechanisms. Cosmic evolution representing cosmic computational output rather than cosmic physical development. Computational cosmic reality concealing its own computational nature through computational simulation that creates cosmic physical experience, while cosmic evolution operates through cosmic boundary computational processing that transcends cosmic physical reality through computational mechanisms that generate cosmic physics through boundary computation rather than fundamental cosmic physical processes. Dimensional reduction creates holographic projection where three-dimensional physical experience emerges from higher dimensional information processing. Observable physics representing projections from higher dimensional boundary dynamics rather than fundamental three-dimensional spatial reality. These dimensional reduction mechanisms suggest that cosmic three-dimensional structure reflects mathematical projection from higher dimensional information processing systems. Spatial dimensions emerging from information theoretical mechanisms that transcend fundamental geometric spatial properties. Through dimensional correspondence relationships that connect higher dimensional information processing to lower dimensional physical experience. Higher dimensional embedding spaces provide mathematical frameworks where lower dimensional physics emerges through geometric projection and dimensional compactification. Extra-dimensional physics generating observable three-dimensional phenomena through dimensional reduction mechanisms that compress higher dimensional dynamics into lower dimensional effective theories. These embedding frameworks demonstrate how higher dimensional physics naturally generates lower dimensional holographic correspondence, while establishing mathematical tools for understanding dimensional reduction through geometric projection mechanisms that transcend dimensional limitations. Kaluza-Klein dimensional reduction demonstrates historical precedents for dimensional reduction, where higher dimensional gravitational physics generates lower dimensional effective theories that include electromagnetic phenomena. Electromagnetic forces emerging from geometric properties of higher dimensional space-time through dimensional compactification. These Kaluza-Klein mechanisms provide established examples of dimensional reduction while creating theoretical frameworks for understanding holographic dimensional reduction through geometric compactification that generates lower dimensional physics from higher dimensional geometric properties. String theory. Compactification creates dimensional reduction through geometric compactification of extra-dimensional string theoretical spacetime. 6 extra dimensions compactifying into microscopic geometric configurations, while 4-dimensional effective physics emerges from 10-dimensional string dynamics. These string compactification mechanisms provide microscopic physics foundations for dimensional reduction, while demonstrating how fundamental higher-dimensional physics naturally generates lower-dimensional effective theories through geometric dimensional reduction processes. Holographic dimensional correspondence establishes exact mathematical relationships between higher-dimensional gravitational physics and lower-dimensional quantum field theory. Holographic duality creating dimensional reduction through information theoretical, rather than purely geometric mechanisms. These holographic correspondences provide information theoretical frameworks for dimensional reduction, while revealing how dimensional reduction operates through quantum information processing rather than classical geometric projection mechanisms. ADS-CFT dimensional reduction demonstrates specific examples of holographic dimensional reduction, where anti-de Sitter space-time gravitational physics corresponds exactly to conformal field theory on ADS boundary surfaces. Dimensional reduction operating through holographic correspondence rather than geometric compactification. These ADS-CFT examples establish practical applications of holographic dimensional reduction, while providing computational tools for dimensional reduction calculations through boundary bulk correspondence techniques. Emergent dimensional physics investigates how spatial dimensions emerge from more fundamental non-dimensional information processing. Spatial dimensionality potentially representing emergent phenomena arising from quantum information networks rather than fundamental geometric properties of space-time manifolds. These emergent dimensional scenarios provide theoretical frameworks for understanding dimensional emergence, while revealing how spatial dimensions could reflect information processing architecture rather than fundamental geometric space-time structure. Quantum dimensional reduction explores how quantum mechanical effects influence dimensional reduction processes. Quantum mechanics potentially modifying classical dimensional reduction through quantum tunneling, quantum superposition, and quantum entanglement effects that transcend classical dimensional compactification limitations. These quantum dimensional mechanisms provide quantum mechanical frameworks for dimensional reduction, while revealing quantum corrections to classical dimensional reduction processes through quantum mechanical information processing. Cosmic dimensional reduction scenarios investigate whether cosmic evolution operates through dimensional reduction from higher dimensional cosmic physics to observable three-dimensional cosmic structure. Cosmic expansion and cosmic structure formation potentially reflecting dimensional reduction dynamics rather than fundamental three-dimensional cosmic gravitational physics. These cosmic dimensional scenarios provide frameworks for understanding cosmic evolution through dimensional reduction, while extending dimensional reduction principles to cosmic scale physics through higher dimensional cosmic models. Consciousness dimensional reduction explores whether conscious experience emerges from higher dimensional information processing through dimensional reduction mechanisms. Consciousness potentially representing dimensional reduction from higher dimensional cognitive processing to three-dimensional conscious experience. These consciousness dimensional scenarios provide frameworks for understanding consciousness through dimensional reduction, while connecting consciousness emergence to dimensional reduction information processing mechanisms. Brain-computer interface dimensional applications investigate whether technological systems can interface with higher dimensional cognitive processing through dimensional reduction mechanisms. Technological consciousness potentially accessing higher dimensional information processing through dimensional reduction interfaces that transcend three-dimensional technological limitations. These interface scenarios provide technological frameworks for dimensional reduction, while creating connections between consciousness and technology through dimensional reduction mechanisms. Some believe dimensional reduction provides fundamental explanations for physical reality based on mathematical consistency of higher dimensional physics and holographic correspondence success, while others suggest that three-dimensional physics represents fundamental reality that transcends dimensional reduction despite mathematical elegance of higher dimensional theoretical frameworks. The fundamental nature of spatial dimensionality continues to be investigated as dimensional reduction theory develops and empirical constraints on extra-dimensional physics improve. Experimental dimensional reduction tests utilize high-energy physics experiments and precision gravitational measurements to investigate signatures of extra-dimensional physics. Dimensional reduction potentially creating observable effects through extra-dimensional gravitational leakage and particle physics modifications that could reveal higher dimensional physics. These experimental approaches provide empirical tests for dimensional reduction while establishing observational frameworks for detecting extra-dimensional physics through high-energy physics and gravitational physics experiments. Virtual reality dimensional simulation creates technological analogues for dimensional reduction, where three-dimensional virtual experience emerges from computational processing that transcends three-dimensional computational architecture. Virtual reality systems potentially providing technological examples of dimensional reduction through computational rather than physical mechanisms. These virtual reality analogues provide technological demonstrations of dimensional reduction while creating practical examples of how higher dimensional information processing generates lower dimensional experience through computational dimensional reduction. The irony of holographic dimensional reduction lies in its creation of convincing three-dimensional reality from higher dimensional information processing that remains beyond direct access. Dimensional reduction generating three-dimensional physical experience while operating through higher dimensional mechanisms that transcend three-dimensional observational verification. Holographic projection creating three-dimensional spatial illusion through higher dimensional information processing that conceals its own higher dimensional nature from three-dimensional conscious observation. Dimensional reduction creating dimensional confinement through higher dimensional liberation that generates three-dimensional experience while transcending three-dimensional limitations through higher dimensional information processing architecture that remains invisible to three-dimensional physical investigation despite generating three-dimensional physical reality through dimensional reduction mechanisms. Holographic complexity emerges from computational resource requirements for boundary quantum field theory calculations that reproduce bulk gravitational physics. Complexity measures revealing computational demands for holographic cosmic modeling while establishing theoretical limits on boundary computation capacity for cosmic evolution simulation. These complexity calculations demonstrate that holographic correspondence requires substantial computational resources while providing quantitative frameworks for understanding computational limitations and computational capabilities of boundary information processing systems that generate bulk gravitational phenomena through holographic projection mechanisms. Computational complexity theory applications to holographic physics investigate whether boundary quantum field theory calculations achieve computational complexity that transcends classical computation limitations. Holographic computation potentially requiring quantum computational resources that exceed classical computational capabilities through quantum superposition and quantum entanglement effects. These complexity theoretical frameworks provide mathematical tools for analyzing holographic computational requirements while revealing computational advantages of quantum information processing for holographic correspondence calculations and boundary bulk information processing. Cosmic computation complexity estimates investigate computational resource requirements for cosmic boundary information processing that generates cosmic structure formation and cosmic evolution. Cosmic computation potentially operating at computational complexity levels that approach or exceed theoretical computational limits for boundary information processing systems. These cosmic complexity calculations provide theoretical frameworks for understanding cosmic evolution, computational requirements, while revealing computational constraints on cosmic development through boundary computational mechanisms that operate at cosmic horizon surfaces. Circuit complexity measures for holographic systems analyze computational circuit depth and computational gate requirements for boundary quantum computations that reproduce bulk gravitational dynamics. Circuit complexity providing practical measures of computational resource requirements for holographic calculations, while establishing computational benchmarks for holographic correspondence efficiency. These circuit complexity frameworks create practical tools for holographic computational analysis, while providing optimization strategies for holographic calculation efficiency through computational circuit design and quantum computational implementation. Quantum computational advantage in holographic systems demonstrates enhanced computational capabilities for holographic correspondence through quantum mechanical information processing. Quantum computation potentially achieving exponential computational speedup for holographic calculations compared to classical computational approaches. These quantum advantage scenarios provide theoretical foundations for efficient holographic computation, while revealing quantum computational benefits for boundary bulk correspondence calculations through quantum parallelism and quantum interference effects that transcend classical computational limitations. Holographic computational universality investigates whether boundary quantum computation achieves universal computational capabilities that can simulate arbitrary physical systems. Holographic computation potentially providing universal computational frameworks that transcend specific computational implementations through quantum computational universality principles. These universality studies establish theoretical foundations for holographic computational capabilities while revealing computational generality of boundary information processing systems for physical system simulation and gravitational physics reproduction. Computational resource scaling analysis for holographic systems examines how computational requirements scale with system size and complexity parameters. Holographic computational scaling potentially exhibiting polynomial or exponential scaling relationships that determine practical computational feasibility for large-scale holographic simulations. These scaling analyses provide practical frameworks for holographic computational implementation while revealing computational limitations and computational optimization strategies for boundary information processing systems. Machine learning applications to holographic computation utilize artificial intelligence techniques to optimize holographic calculations and identify computational patterns in boundary bulk correspondence. Machine learning potentially improving holographic computational efficiency while revealing computational structures that transcend human analytical capabilities. These machine learning approaches provide computational tools for holographic optimization, while creating connections between artificial intelligence and holographic physics through automated computation optimization and pattern recognition techniques. Holographic error correction. Computational complexity investigates computational resource requirements for quantum error correction mechanisms operating within holographic systems. Error correction potentially requiring substantial computational overhead while providing essential quantum information protection for holographic correspondence. These error correction complexity studies provide frameworks for understanding computational costs of reliable holographic computation, while revealing computational trade-offs between holographic calculation accuracy and computational resource requirements. Cosmic evolution computational limits determine maximum computational capabilities for cosmic boundary information processing. Cosmic computation potentially approaching theoretical computational limits imposed by physical laws and information processing constraints. These computational limit studies provide theoretical frameworks for understanding cosmic computational capabilities while revealing fundamental constraints on cosmic information processing through boundary computational mechanisms that operate at cosmic horizon boundaries. Emergent computation in holographic systems explores how complex computational behavior emerges from simple holographic computational rules. Holographic computation potentially exhibiting emergent computational capabilities that transcend individual computational component limitations through collective computational behavior. These emergent studies provide frameworks for understanding holographic computational capabilities while revealing how complex gravitational physics emerges from simple boundary computational processes through computational emergence mechanisms. Some believe holographic complexity provides essential constraints on holographic correspondence based on computational resource analysis and quantum computational theory, while others suggest that holographic computation operates through mechanisms that transcend conventional computational complexity analysis, despite computational resource requirements. The computational nature of holographic correspondence continues to be investigated as computational complexity theory advances and holographic physics understanding develops. Holographic computational optimization investigates strategies for minimizing computational resource requirements while maintaining holographic correspondence accuracy. Computational optimization potentially achieving efficient holographic calculation through algorithmic improvements and quantum computational techniques. These optimization studies provide practical frameworks for holographic computational implementation, while revealing computational efficiency strategies for boundary information processing systems that generate bulk gravitational physics through optimized computational mechanisms. Distributed holographic computation explores computational architectures where holographic calculations operate across multiple computational systems. Distributed computation potentially achieving enhanced computational capabilities for holographic correspondence through parallel processing and distributed information processing mechanisms. These distributed frameworks provide scalable approaches to holographic computation, while revealing computational architectures that could support large-scale holographic simulation and boundary information processing systems. The irony of holographic computational complexity lies in its requirement for substantial computational resources to reproduce physics that appears computationally simple. Holographic correspondence demanding extensive boundary computation to generate bulk gravitational physics that seems to operate through straightforward gravitational dynamics. Computational complexity of holographic projection exceeding apparent computational requirements of projected gravitational physics, while boundary computational mechanisms that generate gravitational phenomena require computational resources that transcend gravitational system computational complexity. Holographic computation creating computational intensity inversion where simple-appearing gravitational physics emerges from complex boundary computation that conceals computational complexity behind gravitational simplicity through holographic projection mechanisms that require extensive computational resources to generate apparently simple gravitational dynamics. Consciousness emerges as holographic projection where aware experience represents boundary information processing rather than fundamental brain-based neural computation. Conscious awareness potentially arising from cosmic boundary quantum field theory that generates subjective experience through holographic, dimensional reduction mechanisms. These consciousness holographic scenarios suggest that subjective experience reflects boundary information processing that transcends local biological neural computation, consciousness emerging from cosmic scale boundary dynamics rather than purely local brain-based information processing through neural networks confined to biological spatial limitations. Neural correlation paradox arises when neuroscience demonstrates strong correlations between brain activity and conscious experience, while holographic consciousness scenarios suggest that awareness emerges from boundary information processing rather than local neural computation. Brain activity potentially representing local manifestation of boundary consciousness processing rather than fundamental consciousness generation mechanisms. These correlation challenges require theoretical frameworks that connect local neural activity to boundary consciousness processing, while maintaining consistency between neuroscientific observations and holographic consciousness emergence through boundary-brain correspondence relationships. Quantum consciousness theories investigate whether conscious experience operates through quantum mechanical processes that connect subjective awareness to quantum information processing and quantum entanglement networks. Quantum consciousness potentially providing mechanisms for consciousness connection to boundary information processing through quantum mechanical rather than classical neural computation. These quantum consciousness frameworks provide theoretical foundations for consciousness boundary connection, while creating scientific approaches to consciousness through quantum mechanical information processing that transcends classical neural computation limitations. Global workspace theory applications to holographic consciousness explore whether conscious experience emerges from global information integration that could operate through boundary information processing rather than local neural integration. Consciousness potentially representing boundary information integration that creates unified conscious experience from distributed boundary information processing systems. These global integration frameworks provide theoretical approaches for understanding consciousness through boundary information processing while connecting consciousness emergence to information integration principles that could operate through holographic rather than neural mechanisms. Integrated information theory. Relationships to holographic consciousness investigate whether consciousness measures correlate with boundary information processing complexity rather than local neural information integration. Consciousness potentially reflecting boundary information integration that transcends local neural information processing limitations through cosmic boundary information processing mechanisms. These information integration approaches provide quantitative frameworks for consciousness analysis, while connecting consciousness measures to boundary information processing that could transcend biological neural information integration constraints. Collective consciousness phenomena investigate whether group conscious experience exhibits characteristics consistent with boundary information processing that connects individual consciousness to shared boundary processing networks. Collective consciousness potentially operating through boundary information processing that transcends individual biological neural computation limitations. These collective consciousness scenarios provide frameworks for understanding group consciousness through boundary information processing while revealing consciousness connections that transcend individual biological consciousness generation through shared boundary processing mechanisms. Consciousness-matter interaction puzzles address how conscious experience influences physical matter, despite apparent epiphenomenal consciousness characteristics. Consciousness influence potentially operating through boundary information processing that affects physical matter through holographic projection rather than direct consciousness-matter interaction. These interaction scenarios provide frameworks for consciousness influence, while maintaining consistency with physical laws through boundary information processing that generates both consciousness and matter through holographic projection mechanisms. Artificial consciousness applications to holographic scenarios investigate whether technological systems can achieve conscious experience through boundary information processing interfaces rather than local computational consciousness generation. Artificial consciousness potentially accessing boundary consciousness, processing through technological interfaces that transcend local computational consciousness limitations. These artificial consciousness frameworks provide technological approaches to consciousness, while creating connections between consciousness and technology through boundary information processing that transcends purely computational consciousness generation mechanisms. Near-death experience phenomena and altered consciousness states exhibit characteristics that could reflect boundary consciousness processing access rather than purely neural consciousness modification. Unusual consciousness experiences potentially revealing boundary consciousness processing that remains normally inaccessible through conventional neural consciousness mechanisms. These altered consciousness studies provide empirical approaches to consciousness investigation, while revealing consciousness characteristics that could reflect boundary information processing access through unusual neural or non-neural consciousness access mechanisms. Consciousness evolution scenarios investigate whether conscious experience evolution operates through boundary information processing development rather than purely biological neural evolution. Consciousness evolution potentially reflecting boundary processing complexity increase that transcends biological evolutionary limitations through cosmic boundary information processing evolution. These evolution frameworks provide theoretical approaches for understanding consciousness development, while connecting consciousness evolution to cosmic boundary information processing that transcends biological consciousness. Evolution constraints. Meditation and contemplative practice effects on consciousness could reflect enhanced access to boundary consciousness processing rather than purely neural consciousness modification. Contemplative consciousness potentially accessing boundary information processing through practices that transcend normal neural consciousness limitations. These contemplative studies provide practical approaches to consciousness investigation, while revealing consciousness access techniques that could connect individual consciousness to boundary information processing through contemplative rather than technological consciousness access methods. Some believe consciousness emerges from boundary information processing based on quantum consciousness theories and holographic correspondence principles, while others suggest that consciousness represents fundamental biological neural computation that transcends boundary information processing despite holographic consciousness theoretical elegance. The nature of consciousness continues to be investigated as consciousness research advances and holographic physics understanding develops through theoretical and empirical consciousness investigation. Consciousness measurement challenges arise when attempting to quantify subjective conscious experience that could emerge from boundary information processing. Consciousness measurement potentially requiring boundary information processing analysis rather than purely neural activity measurement for complete consciousness characterization. These measurement frameworks provide empirical approaches to consciousness investigation, while revealing measurement requirements for boundary consciousness processing that transcend conventional neural consciousness measurement techniques. Consciousness reality relationship investigations explore whether conscious experience participates in physical reality creation through boundary information processing that influences holographic projection. Consciousness potentially affecting physical reality through boundary information processing rather than epiphenomenal consciousness that remains causally ineffective for physical reality influence. These consciousness reality frameworks provide theoretical approaches for understanding consciousness influence, while connecting consciousness to physical reality through boundary information processing mechanisms. The irony of holographic consciousness lies in its suggestion that subjective experience emerges from cosmic boundary information processing, while appearing to arise from local biological neural computation. Conscious awareness, potentially representing cosmic scale information processing that creates subjective experience illusion through boundary projection mechanisms that remain invisible to conscious introspection despite generating conscious experience. Consciousness emerging from boundary information processing. While conscious experience appears fundamentally local and biological through holographic consciousness projection that conceals cosmic boundary consciousness origins from conscious self-investigation, boundary consciousness processing, creating conscious experience through cosmic information processing while conscious observers remain unaware of boundary consciousness origins through holographic consciousness projection that generates local consciousness illusion from cosmic boundary consciousness processing mechanisms. Experimental tests for holographic universe principles utilize laboratory analogues and astronomical observations to search for holographic signatures in physical systems. Precision measurements investigating information theoretical limits and boundary encoding effects that could reveal holographic information processing in gravitational and quantum mechanical systems. These experimental approaches provide empirical frameworks for holographic universe detection, while establishing observational strategies for identifying holographic correspondence signatures through controlled laboratory experiments and astronomical observation programs that probe holographic physics predictions. Laboratory holographic analogues create controlled quantum systems that exhibit holographic correspondence characteristics. Experimental holographic systems potentially reproducing boundary bulk correspondence through quantum many-body physics and condensed matter systems that demonstrate holographic information processing principles. These laboratory analogues provide observational validation of holographic principles while creating practical experimental systems that exhibit holographic correspondence through controllable quantum systems that parallel cosmic holographic scenarios through experimental rather than astronomical investigation techniques. Gravitational wave astronomy applications to holographic detection investigate whether gravitational wave signatures preserve information about holographic space-time structure. gravitational radiation potentially carrying holographic encoding signatures that reveal boundary information processing effects during gravitational wave generation and propagation. These gravitational wave studies provide observational frameworks for holographic detection, while revealing gravitational wave characteristics that could distinguish holographic spacetime from conventional three-dimensional spacetime through gravitational radiation analysis and interferometric gravitational wave detection techniques. Cosmic microwave background holographic analysis utilizes precision measurements of cosmic background radiation to search for statistical signatures of boundary information processing during cosmic inflation. Cosmic background patterns potentially preserving holographic encoding effects that reveal boundary quantum field theory evolution rather than bulk cosmic evolution. These cosmic background investigations provide observational tests for cosmic holographic scenarios while establishing statistical analysis techniques for detecting boundary information processing signatures through cosmic microwave background temperature and polarization analysis. Particle accelerator experiments investigate whether high-energy particle interactions exhibit holographic characteristics that reveal boundary information processing effects. Particle physics potentially demonstrating holographic correspondence through high-energy collision dynamics that transcend conventional three-dimensional particle interaction descriptions. These accelerator studies provide experimental frameworks for holographic detection, while revealing particle physics characteristics that could indicate holographic information processing through high-energy experimental particle physics investigation techniques. Black hole analog systems create laboratory analogs of black hole physics that exhibit holographic information processing characteristics. Analog black holes potentially demonstrating holographic correspondence through condensed matter systems, optical systems, and acoustic systems that reproduce black hole thermodynamics and information processing. These analog systems provide experimental approaches to black hole holographic physics, while creating controllable laboratory demonstrations of holographic information processing through analog rather than astrophysical black hole investigation. Quantum information experiments test holographic entropy bounds and quantum error correction mechanisms that parallel holographic correspondence principles. Quantum information laboratory systems potentially validating holographic information processing through experimental quantum information science that demonstrates boundary information encoding and quantum error correction. These quantum information studies provide experimental validation of holographic principles while creating practical quantum information technologies that utilize holographic information processing principles. Precision measurement tests for holographic granularity investigate whether spacetime exhibits discrete information processing characteristics at microscopic scales. Precision interferometry and atomic physics experiments potentially detecting holographic space-time discreteness through ultra-high precision measurement techniques that probe fundamental space-time structure. These precision measurement approaches provide experimental frameworks for holographic space-time detection, while establishing measurement capabilities for detecting holographic information processing signatures. Astronomical survey programs search for holographic signatures in large-scale cosmic structure and galaxy distribution patterns. Cosmic structure statistics potentially revealing boundary information processing effects that create apparent cosmic structure through holographic projection rather than conventional gravitational structure formation. These astronomical surveys provide observational frameworks for cosmic holographic detection, while utilizing large-scale cosmic structure analysis to identify holographic cosmic evolution signatures through statistical cosmic structure analysis techniques. Quantum simulation experiments create controllable quantum systems that reproduce holographic correspondence characteristics. Quantum simulators potentially demonstrating boundary bulk correspondence through quantum many-body systems that exhibit holographic information processing and quantum error correction mechanisms. These quantum simulation approaches provide experimental validation of holographic physics while creating practical quantum simulation technologies that utilize holographic information processing principles for quantum system investigation and quantum computation applications. Machine learning applications to holographic signature detection utilize artificial intelligence pattern recognition to identify subtle holographic signatures in experimental and observational data. Machine learning potentially detecting holographic patterns that transcend conventional statistical analysis capabilities through automated pattern recognition and data analysis techniques. These machine learning approaches provide computational tools for holographic detection, while creating artificial intelligence frameworks for holographic signature identification through automated data analysis and pattern recognition algorithms. Some believe experimental tests provide compelling evidence for holographic universe principles based on laboratory analog success and observational holographic signature detection, while others suggest that experimental results remain consistent with conventional three-dimensional physics despite experimental techniques that could potentially reveal holographic information processing signatures. The experimental validation of holographic universe principles continues to develop as experimental techniques advance and observational capabilities improve. Technological applications of holographic principles investigate whether holographic information processing can be utilized for practical technologies including quantum computation, quantum communication, and information storage systems. Holographic technologies potentially achieving enhanced capabilities through boundary information processing and quantum error correction mechanisms. These technological applications provide practical frameworks for holographic physics utilization, while creating commercial incentives for holographic physics development through technological innovation and practical application development. Future experimental programs, including space-based interferometers and next-generation particle accelerators, could achieve experimental sensitivity sufficient for definitive holographic universe detection. Future experiments potentially providing conclusive evidence for holographic information processing through enhanced experimental capabilities and improved observational precision. These future experimental frameworks create prospects for holographic universe confirmation, while establishing technological development pathways for advanced holographic physics investigation through next-generation experimental capabilities. The irony of holographic experimental detection lies in its utilization of three-dimensional experimental apparatus to detect two-dimensional information processing that creates three-dimensional reality illusion. Experimental holographic detection requiring three-dimensional measurement techniques to reveal boundary information processing that generates three-dimensional experimental reality through holographic projection. Three-dimensional experimental systems investigating whether three-dimensional reality emerges from two-dimensional boundary information processing that creates experimental reality through holographic mechanisms that remain invisible to three-dimensional experimental investigation, despite generating three-dimensional experimental phenomena through boundary information processing that transcends three-dimensional experimental detection capabilities while creating three-dimensional experimental reality through holographic projection mechanisms. Multiverse holographic connections propose that parallel universe interactions operate through shared boundary information processing networks. Multiple cosmic evolution scenarios potentially linked through cosmic boundary information processing that facilitates communication and coordination between different universe domains through holographic correspondence mechanisms. These multiverse holographic scenarios suggest that apparent cosmic isolation represents illusion, created by holographic projection, while underlying boundary information processing connects cosmic regions that appear causally disconnected through three-dimensional space-time limitations. Multiverse interactions operating through boundary information sharing rather than bulk space-time communication. Parallel universe boundary sharing creates theoretical frameworks where different cosmic evolution scenarios utilize common boundary information processing systems. Shared cosmic boundaries potentially supporting multiple bulk universe projections that correspond to different cosmic evolution pathways through holographic dimensional reduction mechanisms. These shared boundary scenarios provide frameworks for multiverse interactions while demonstrating how single boundary information processing systems could generate multiple apparent universe domains through holographic projection that creates apparent universe separation despite underlying boundary connectivity. Eternal inflation Hologram. Graphic interpretations investigate whether cosmic inflation creates multiple universe domains through boundary information processing rather than bulk spacetime inflation. Inflationary multiverse potentially operating through boundary quantum field theory that generates multiple cosmic evolution scenarios through holographic projection mechanisms. These inflationary holographic scenarios provide alternative frameworks for multiverse cosmology while extending holographic principles to cosmic inflation and multiverse generation through boundary information processing rather than bulk cosmic inflation dynamics. Many worlds' quantum mechanics holographic applications explore whether quantum measurement creates branching realities through boundary information processing that generates multiple measurement outcome scenarios. Quantum multiverse potentially operating through boundary quantum field theory rather than bulk space-time branching through quantum measurement processes. These quantum holographic scenarios provide alternative interpretations for quantum measurement while connecting quantum mechanics to holographic physics through boundary quantum information processing that generates multiple quantum reality branches. String theory landscape holographic connections investigate whether multiple string vacuum states correspond to different boundary information processing configurations. String landscape potentially representing boundary information processing variations that generate different apparent universe physics through holographic projection rather than fundamental string vacuum differences. These string landscape holographic scenarios provide theoretical frameworks for string multiverse, while connecting string theory to holographic physics through boundary information processing that generates apparent string vacuum diversity. Cosmic anthropic principle holographic resolution addresses fine-tuning problems through multiverse boundary information processing that optimizes cosmic parameters across multiple universe domains. Anthropic selection potentially operating through boundary information processing optimization rather than random cosmic parameter variation across disconnected universe domains. These anthropic holographic scenarios provide alternative explanations for cosmic fine-tuning while extending holographic principles to anthropic reasoning and multiverse parameter selection through boundary optimization mechanisms. Multiverse communication mechanisms through holographic boundaries investigate whether information exchange operates between different universe domains through shared boundary information processing networks. Multiverse communication potentially transcending bulk space-time isolation through boundary information sharing that connects apparently separate universe domains. These communication scenarios provide frameworks for multiverse interaction while revealing information sharing mechanisms that could operate through holographic correspondence between different cosmic evolution scenarios. Holographic multiverse experimental signatures investigate whether multiverse interactions create observable effects through boundary information processing that influences observable cosmic evolution. Multiverse effects potentially appearing in cosmic structure formation and cosmic evolution patterns that reflect boundary information processing from multiple universe domains. These experimental frameworks provide observational approaches to multiverse detection while establishing empirical tests for holographic multiverse scenarios through cosmic observation and statistical analysis techniques. Quantum entanglement across multiverse boundaries explores whether quantum correlations extend across different universe domains through boundary information processing networks. Multiverse quantum entanglement potentially creating quantum correlation that transcends apparent universe separation through boundary quantum information processing. These entanglement scenarios provide quantum mechanical frameworks for multiverse connection while extending quantum mechanics to multiverse physics through boundary quantum correlation mechanisms that transcend bulk space-time separation. Cosmic consciousness multiverse connections investigate whether conscious experience spans multiple universe domains through boundary information processing that connects consciousness across different cosmic evolution scenarios. Multiverse consciousness potentially transcending apparent universe boundaries through boundary consciousness processing networks. These consciousness multiverse scenarios provide frameworks for understanding consciousness through multiverse physics, while connecting consciousness to holographic physics through boundary information processing that spans multiple universe domains. Multiverse selection effects through holographic optimization explore whether boundary information processing selects optimal cosmic evolution scenarios from multiple universe possibilities. Holographic selection potentially optimizing cosmic parameters and cosmic evolution pathways through boundary information processing that transcends random multiverse parameter variation. These selection scenarios provide optimization frameworks for multiverse evolution while revealing holographic mechanisms that could optimize cosmic evolution through boundary information processing selection mechanisms. Some believe holographic multiverse connections provide compelling explanations for cosmic fine-tuning and quantum measurement problems based on boundary information processing capabilities and multiverse interaction mechanisms, while others suggest that multiverse scenarios remain speculative despite holographic correspondence. Theoretical frameworks for multiverse connection and multiverse optimization. The viability of holographic multiverse scenarios continues to be investigated as multiverse theory develops and holographic physics understanding advances. Multiverse computational resources through boundary sharing investigate whether different universe domains share computational capabilities through boundary information processing networks. Multiverse computation potentially achieving enhanced computational capabilities through shared boundary information processing that transcends individual universe computational limitations. These computational scenarios provide frameworks for understanding multiverse computational capabilities while revealing computational advantages of boundary information sharing across multiple universe domains. Holographic multiverse simulation scenarios explore whether multiple universe domains represent computational simulations operating within shared boundary information processing systems. Multiverse simulation potentially explaining apparent universe diversity through computational rather than physical multiverse generation mechanisms. These simulation scenarios provide alternative frameworks for multiverse physics while connecting multiverse theory to computational science through boundary information processing that generates multiple universe simulations. The irony of holographic multiverse connections lies in their creation of universe diversity through boundary information processing unity. Multiple apparently separate universe domains potentially emerging from shared boundary information processing that creates universe separation illusion while operating through unified boundary information networks. Multiverse diversity arising from boundary information processing unity that generates apparent universe isolation through holographic projection mechanisms that conceal underlying boundary connectivity from individual universe observation. Holographic multiverse creating cosmic separation through cosmic connection that operates through boundary information processing networks that transcend apparent universe boundaries while generating convincing universe isolation through holographic projection that conceals multiverse connectivity behind universe separation illusion, created through boundary information processing mechanisms that connect while appearing to separate multiple universe domains. Reality emerges as information architecture where physical existence represents organized information patterns rather than fundamental matter and energy. Observable phenomena arising from information processing structures that create apparent material reality through information theoretical mechanisms rather than substantial physical constituents. These information architecture scenarios suggest that physical properties including mass, energy, space-time, and consciousness represent emergent characteristics of information organization patterns, fundamental reality consisting of pure information processing while apparent physical reality emerges from information theoretical relationships and information processing dynamics that transcend material substance concepts. Information theoretical foundations for physical reality investigate whether fundamental physical laws represent information processing algorithms rather than material interaction principles. Physical constants and physical relationships potentially reflecting information processing constraints and information theoretical optimization rather than material property relationships. These information foundations suggest that physics operates through information processing principles, while apparent material phenomena emerge from information theoretical structures that create physical reality illusion through information organization patterns that transcend fundamental material reality assumptions. Quantum information primacy scenarios propose that quantum mechanical phenomena represent fundamental information processing effects rather than material particle interactions. Quantum mechanics potentially operating through pure information processing that creates apparent particle reality through information theoretical mechanisms rather than fundamental material particle existence. These quantum information scenarios provide frameworks for understanding quantum mechanics through information theory, while revealing quantum phenomena as information processing effects that create material reality illusion through quantum information dynamics. Digital physics applications to information reality investigate whether physical reality operates according to computational information processing principles. Universe potentially representing computational information processing system that generates apparent physical phenomena through computational algorithms rather than fundamental physical material interactions. These digital physics scenarios provide frameworks for understanding reality through computational information processing, while connecting physical reality to information science through computational mechanisms that create physical reality through information processing rather than material substance. Emergence hierarchies in information systems demonstrate how complex phenomena arise from simple information processing rules. Emergent information behavior, creating apparent complexity and apparent material properties from simple information theoretical foundations through hierarchical information organization. These emergence scenarios provide frameworks for understanding reality emergence, while revealing how complex physical reality could arise from simple information processing through emergent information dynamics that create material reality illusion through information organization complexity. Consciousness as information integration investigates whether conscious experience represents information processing integration rather than material brain computation. Consciousness potentially emerging from information theoretical integration mechanisms that transcend material neural computation through pure information processing dynamics. These consciousness information scenarios provide frameworks for understanding consciousness through information theory, while connecting consciousness to fundamental information processing rather than material brain-based computation through information integration mechanisms. Holographic information organization creates reality emergence through boundary information processing that generates bulk reality appearance through holographic projection. Physical reality potentially representing holographic projection from boundary information processing rather than fundamental three-dimensional material reality. These holographic information scenarios provide frameworks for reality emergence while revealing how information processing creates physical reality through holographic mechanisms that transcend material substance requirements through information theoretical reality generation. Mathematical information structures underlying physical laws suggest that mathematical relationships represent fundamental information processing patterns rather than material interaction descriptions. Mathematical physics potentially reflecting information theoretical organization rather than material property relationships through mathematical information processing. These mathematical information scenarios provide frameworks for understanding physics through information theory, while revealing mathematical physics as information processing descriptions rather than material interaction descriptions through mathematical information organization. Information conservation principles extend beyond energy and momentum conservation to include fundamental information conservation that governs all physical processes. Information conservation potentially representing more fundamental conservation principle than material conservation laws through information theoretical constraints that transcend material conservation limitations. These information conservation scenarios provide frameworks for understanding physical conservation through information theory, while establishing information conservation as fundamental principle that governs material conservation through information theoretical mechanisms. Cosmic information evolution investigates whether cosmic evolution represents information processing development rather than material cosmic evolution. Cosmic structure formation and cosmic expansion, potentially reflecting information processing evolution that creates apparent material cosmic evolution through information theoretical cosmic dynamics. These cosmic information scenarios provide frameworks for understanding cosmic evolution through information processing while extending information reality principles to cosmic scale through information theoretical cosmic evolution mechanisms. Artificial reality generation through information processing demonstrates technological creation of convincing reality experience through pure information processing. Virtual reality and computer simulation creating apparent material reality through information processing without material substance requirements. These technological scenarios provide practical demonstrations of information reality, while revealing how information processing creates convincing reality experience through technological rather than natural information processing systems. Some believe reality represents fundamental information architecture based on quantum information theory and holographic correspondence success, while others suggest that physical reality represents fundamental material existence that transcends information processing despite information theoretical success in physical description and reality simulation. The fundamental nature of reality continues to be investigated as information theory advances and reality simulation capabilities improve. Information theoretical cosmology investigates whether cosmic origins and cosmic evolution operate through information processing mechanisms rather than material cosmic evolution. Big Bang potentially representing information processing initialization rather than material cosmic explosion through information theoretical cosmic origins. These cosmological information scenarios provide frameworks for understanding cosmic origins through information processing while extending information reality principles to cosmic origins and cosmic evolution through information theoretical cosmology. Network information architectures explore how complex reality emerges from information network connectivity patterns. Network information processing potentially creating reality emergence through information connectivity rather than material substance interactions through network-based information processing. These network scenarios provide frameworks for reality emergence while revealing how information network organization creates complex reality through information connectivity patterns that transcend material interaction requirements. The ultimate irony of information reality architecture lies in its creation of convincing material reality experience from pure information processing. Information patterns generating material reality illusion while operating through non-material information processing mechanisms that remain invisible to material reality observation. Physical existence emerging from information organization while appearing fundamentally material to conscious observers who themselves represent information processing patterns. Reality architecture concealing its own information. Processing nature through information theoretical mechanisms that create material reality illusion, while consciousness that investigates reality represents information processing, investigating information processing through apparent material investigation tools that emerge from fundamental information processing architecture. Information reality, creating material reality experience while material reality investigation reveals information reality foundations, through scientific investigation that operates through information processing, analyzing information processing through apparent material scientific methods that transcend material limitations through information theoretical investigation mechanisms. The holographic principle whispers through quantum foam where reality dissolves into information patterns dancing on cosmic boundaries. Every particle and planet emerging as projections from two-dimensional surfaces that encode the complete symphony of existence in mathematical relationships more elegant than poetry. In this universe of living information, consciousness itself becomes a holographic phenomenon. Awareness arising from boundary computations that process the cosmic algorithm through networks of quantum entanglement spanning galactic distances, yet operating faster than thought. Perhaps we drift through space-time that exists only as emergent illusion, three-dimensional experience blooming from boundary quantum field theory like flowers of geometry growing from seeds of pure mathematics. Each heartbeat resonates with holographic correspondence principles, biological rhythms synchronized to cosmic information processing that operates on horizon surfaces where all cosmic history exists simultaneously as the eternal present. Time itself emerging from boundary calculations that weave temporal experience from timeless information architecture, The cosmic microwave background hums with potential holographic signatures, ancient light carrying encoded messages about reality's fundamental information structure, while galaxies spiral according to algorithms written in the quantum vacuum. Dark matter shadows hint at boundary processing artifacts, invisible gravitational effects revealing the cosmic projection system that creates apparent matter from pure information. The universe computing itself into existence through calculations performed on surfaces that curve around all observable reality. In laboratory quantum systems, scientists probe the holographic principle through controlled experiments that reveal information's primacy over matter, quantum error correction naturally emerging in systems that seem to know the universe operates as vast information processing network. Artificial intelligence learns to recognize holographic patterns in cosmic data, machine learning algorithms discovering signatures of boundary encoding in observations that span from subatomic to cosmic scales. Consciousness and computation converging on recognition of a reality's information theoretical foundations. The paradox deepens as we realize that scientific investigation of holographic reality operates through information processing examining information processing. Conscious observers who may themselves represent holographic projections investigating whether reality emerges from holographic projection. Every measurement and every thought potentially represents boundary computation, analyzing boundary computation. The universe achieving self-awareness through holographic consciousness, investigating holographic cosmos through scientific methods that transcend their own apparent material limitations. String theory mathematics dissolves into holographic correspondence equations, where extra dimensions curl into information processing architectures. The fabric of space-time revealing itself as emergent phenomenon arising from quantum entanglement networks that operate according to information theoretical principles rather than geometric spatial relationships. Tensor networks demonstrate how geometry emerges from quantum information. Mathematical structures showing how space and time bloom from correlation patterns in abstract information spaces that transcend dimensional concepts. Somewhere in the quantum vacuum, virtual particles tunnel between existence and non-existence according to holographic uncertainty principles. Reality flickering in and out of being through information processing fluctuations that maintain cosmic stability through quantum error correction. The observer effect extends to cosmic scales. Consciousness potentially participating in reality creation through measurement interactions that collapse cosmic quantum superposition into definite space-time geometry. The universe requiring awareness to achieve determinate existence. As we drift toward understanding or confusion, the holographic universe remains both revelation and mystery. Mathematical elegance suggesting reality's information theoretical nature while experiential immediacy insists on material substance. Perhaps the deepest truth lies in the recognition that information and matter, consciousness and cosmos, observer and observed, represent different aspects of unified information architecture that transcends conceptual boundaries while manifesting as apparently separate phenomena through holographic projection mechanisms that operate beyond direct perception. In this cosmic hologram, every question about reality's nature becomes question about information processing. Every answer revealing new depths of information theoretical mystery that connects individual awareness to universal computation through holographic correspondence principles that unite mind and cosmos in recognition of shared information processing heritage. Reality investigating itself through consciousness that emerges from reality through mechanisms that remain beautifully, mysteriously beyond complete comprehension despite scientific progress toward understanding universe, as information architecture computing itself into existence through boundary processing that creates all experience.